two parts. We're first going to go over some of the attributes of the NGA-East database, so that's recorded ground motions. So Tadahiro here, who was instrumental in making that work, is going to do an overview of the data that's available in the products. That's going to be followed by a short presentation on magnitude and distance metadata done by Bob Youngs. After that, Joseph Harmon is going to do the presentation for Youssef Ashash, who's trying to get here and his flight was delayed, on how VS30 was assigned to all of those sites. And then I had a 5 minutes that I yanked out of the program because Tada is covering all the important issues there. Then we'll have a short discussion and break, and after that we come back for regionalization. So Tada, thank you.
All right, so hello everybody. My name is Tadahiro Kishida and working as a peer. And I mainly did the database, data processing for the NGA-East database. So I want to explain those database. So the database overview is that we have about 9,500 records. And those are uniformly processed from the 70 earthquake events. And magnitude ranges from 2 to 7. And epicenter distance ranges from 1 kilometer to 3,000 kilo. So it's 3,000 kilometers is very long distance, not 300. And this database includes the Fourier amplitude spectra for different windows and filtered baseline corrected acceleration velocity displacement time series and pseudo-spectral accelerations and duration areas intensities. And then we generate a flat file. So these are in the database. And there are some issues during data processing. So I put this as the challenges and solution in data processing. We saw lots of microseismics during the filtering, so how to handle those microseismics. And also the PSA for low sampling rate records. For example, a TA array and sampling rate is about 40, and the Nyquist frequency is 20 hertz. But we want to calculate like a much shorter the period of response spectra. So we need to do the interpolation for low sampling rates, the records. So how to handle those computation with the PSA. And also in this case, we are calculating FAS. And that goes to the very large, huge data sets. So that we need to handle those large volume data sets. So the first I show the database overview. And this is from the flat file. We plotted the magnitude of the epicenter distance. The y-axis is magnitude, and x-axis is epicentral distance. And there are 6 figures, and one figure is the entire database, and the other figures are coming from the network. So TA is a TA array, US transportable arrays, and that consists of about 50% of the total data. And CN is a Canadian network, and US is a United States seismic network, and NM is a New Madrid network. So these 4 networks covers about 90% of total data. And TA is the main portion of the data, about 50%. And if you see this data, with the increase of the epicentral distance, magnitude increases. So it means like a data set is like a magnitude and distance is correlated. And we don't have the short distance, large magnitude data. And similarly, that we don't have the large distance, small magnitude data. And to do the uniform data processing, we developed one windowing method. And this method is like we first plot the 3-component acceleration, and there are 3 traces. The first component acceleration, second one is the displacement. Acceleration, displacement, acceleration, displacement, and shows the 6 traces. And the first, we select the P wave arrival, then compute the estimated S wave and LG wave arrival. And that shows the orange line here. And the analysts pick the S wave arrival visually by looking at the change of the amplitude acceleration and change of the amplitude displacement. Then compute the end of the LG wave and call the windows. And that is based on the hypocenter distance and divided by the travel time of the S wave and LG wave, then adding the expected duration of the LG wave, and select the end of the LG wave window, then also putting the additional coda windows at the end of after the SLG wave windows. And this process requires selecting the P wave arrival and S wave arrival, and the other is automatically calculated. And by doing this one, we compute 5 different windows: pre-event noise window, and P wave window, and SLG window, and coda window. And by adding these, we compute the entire windows. And using these 5 windows, we plotted the FAS. And for example, this is the same recording example, and blue is entire FAS. And yellow is the P wave FAS. So P wave has a higher amplitude of the higher frequencies and decrease for the amplitude for low frequencies. And gray is the coda window, and the pink one is a noise window. So noise window has a high amplitude for the high frequencies and decreases and increases some small bump there, about 2 seconds. That is a microseismus. And then decreasing again increases for the low frequencies. And by looking at this figure, we decide where is the place for the high pass corner frequencies and low pass corner frequencies. And if you see this figure, the pink line is overlapping the blue line. It's about 0.02 hertz, and that is selected the high pass corner frequencies. And by using this method, we select the high pass corner frequencies and low pass corner frequencies. So in this example, the high pass corner frequency is applied at 0.02 seconds, so 0.02 hertz, and low pass corner frequency is not applied here. And after applying the filter, we compute the acceleration, velocity, and displacement time series. And by left-hand figure is the acceleration, velocity, and displacement without baseline corrections. And by then, we applied the baseline corrections for right figures. And this computed baseline corrected acceleration, velocity, displacement time series are saved in the output file. And this baseline correction is normally required because we integrate the acceleration time series with the assumption of the initial velocity and displacement equals 0. But after the filter, we have very small velocity and displacement. And that difference of the initial condition makes this lump over the displacement. So it requires baseline corrections. And then after calculating the baseline corrections, we compute the PSA. And this example shows the difference before and after the baseline corrections. But we don't see any such, basically the same. Baseline correction is not affecting anything for the PSA. And maximum difference is less than 1% at 20 hertz. So checking this the effect of baseline corrections. So these PSA are also saved for different damping. So 11 damping starting from the 0.5% damping and increase to up to the 30% of damping. So these are saved in the file. Then we also compute the alias intensity and durations. By using the baseline corrected vehicles, alias intensity durations computed, and those are saved. And those values are saved as a 5%, 10%, and increasing by 5% to 95% of alias intensity and its time. So basically, we can compute any definition of the durations based on the alias intensity. Can be 5%, 95% durations, we can calculate. 5%, 75% duration, we can calculate. Because each 5%, we are saving the time in the output file. And maybe another thing I want to mention is that if you see the time, this is one example about 1,000 kilometers. It says 600 seconds, means 10 minutes. And it's about 1,000 kilometers, it shows like 10 minutes. So it goes to 1,000 kilo, it goes more, like 20 minutes or more than that. So the entire record length is very long. And then after making these output files, we combine those, we make the flat file. And flat file consists of these data columns. And the pink one is the information related to earthquake source. So the earthquake ID, earthquake name, and those data are listed in the pink columns. Then we have the site database information, station sequence number, and station information like latitude, longitude, and some VS30. So those are worked by the different working groups. And this other data is the propagation path. So the distance from the epicenter distance, hypocenter distance, going to the earthquake region number and the station region number. So regionalization issues is related to the propagation path, the columns. And the last part, the record related to the record catalog, and these are the work I mainly worked on. So the related to the data process results. So file name and the sampling rate and high-pass, low-pass filter, corner frequencies, and microseisms. So these different, the 4 different data sources are combined and going to the flat file. So these are created. Then after making the flat file, I plotted just for confirmation purpose, the low-pass corner frequency and magnitude, and for different network. And if you see these data, we don't see any the correlations between the low-pass corner frequencies and magnitude. And it makes sense because the high frequency amplitude is less dependent on the magnitude. So that we select the corner frequencies, but that result doesn't depend on the magnitude. And also, if you see this data, the upper bound of the TA array looks about like 20 hertz. Right? So it means like the sampling rate is 40 and NIX is 20. Most of the data for TA arrays, NIX is 20 hertz. And if I plot this data against the epicenter distance, we see the trend. The low-pass corner frequency decreases with the increase of the epicenter distance because the high frequency amplitude decreases with distance. So this trend is reflected for the selected corner frequencies by looking at the signal to noise ratio to the amplitude of the signal to the noise. We are picking up the low-pass corner frequencies. But selection looks reasonable after plotting the result from the flat file. And also, I plotted the high-pass corner frequency against magnitude. And if you see these figures, the high-pass corner frequencies decreases as magnitude increases. And it makes sense because the low frequency amplitude increases with magnitude. So if we have the larger magnitude and we're selecting the high-pass corner frequencies, but that's expanding the low frequency context with the increase of magnitude. So that this result looks reasonable for me. And the last figure is that I plotted the high-pass corner frequency similar with the epicentral distance. And if you see this figure, the high-pass corner frequency decreases with the increase of the epicentral distance. And it means that with the distance longer and longer, low frequency components becomes more good signals. And it doesn't make sense. And that the reason is that the first I showed that the magnitude and the epicenter distance is correlated in the database. So that means that increase of the epicenter distance means increase in the magnitude. So these observations explain that the correlation in the database, the magnitude and distance, we don't have the short epicenter distance, large magnitude data. And also, we don't have the long distance and small magnitude data in database. So these correlations generated correlated high-pass corner frequencies and epicenter distance. Okay, so I explained this is an overview of the processing data and flat file, and the data and some next things I want to explain the challenges and solutions in data processing. There are three things here: the microseisms and PSA for low sampling rate records and data volume. The first thing is the microseisms, and for many cases, there are many long-distance records. So we see the microseisms, and that is affecting FAS for the limited range of the Fourier spectrum. And if you see this figure, the blue one is entire FAS, and pink one is the microseisms. And if you see this figure, the microseism is pushing up some limited ranges of the Fourier spectrum. And below the microseisms, actually there's a usable ranges. So if we cut the higher bound of the microseisms, we are going to discard all the data lower than that ranges. But actually, we want to utilize some portion of the low frequency contents that is not affected by the microseisms. So for that data processing, we kept the microseisms in data and selected the high-pass corner frequency based on the signal-to-noise ratio. But we assigned the range of the microseisms in the flat file. So it means that we can rely, the data is rely on up to the lower to the microseisms, but some limited range cannot be, maybe not be used because that range is affected by microseisms. So we did this data processing to treat the microseisms. And the next thing is we have lots of low sampling rate records for TA array, mainly TA array, 40 Hertz sampling rate, 20 Hertz Nyquist. And for this case, we need to compute the PSA, but that period of the PSA is kind of 0.01 second or something. And normally, we interpolate the time series by 1/10. DT becomes to 1/10 over the period of the structures. And there are two things we can do this here is that interpolation, how we interpolate the data. And the blue square is original data in this example figure. And red line is the example of the linear interpolations. By using linear interpolation, we can pick any DT. And also the open circle is the sync interpolations. And this sync interpolation is that we first calculate FAS, then padding the zero amplitude above the Nyquist frequencies, and move to the Nyquist frequency higher, and go back to the time series. So we can interpolate that by using for the new Nyquist frequencies. And by doing this sync interpolation, we can get like a more smooth time domain interpolations. And this example shows the difference between linear interpolation and sync interpolation PSA. And the right-hand side figure is that the dashed line is a sync interpolation, and the solid line is a linear interpolations. And actually, there is a difference near the Nyquist frequencies. And slightly higher, above the Nyquist frequencies, the sync interpolation goes higher than the linear interpolations. But lower than in the periods, lower than the Nyquist frequencies, it goes slightly smaller. And the right-hand side figure is showing the ratio between PSA by sync over the PSA by linear. And it makes, if we see the log scale, we don't see such a big difference. But if we see that by taking the ratio, it goes about 30% near the Nyquist. And this number is maybe not so small. And we need to define the methodology, how to interpolate. And the sync interpolation is recommended for our study based on the Dave and Christine. So we followed the sync interpolations for how to compute the PSA for the low sampling rate time series. Okay, and data volume. And this goes very large for FAS, especially. And one reason is that duration is very long. And the other reason is that we want to make the same, like a DF, the frequency steps in the output file, because that makes easier for post-processing computation, smoothing, and compute the using for the FAS. So for these reasons, we padding the zero for the specified length of the record. For example, if I have the DT of 0.1, that data is padded, and duration goes to about 3,200 seconds. It's about 50 minutes. So if we have the 10 minutes or 20 minutes record, padding zero, and go to 50 minutes, and then calculate FAS. And for the different time series, we always keep the same length of the padding before taking the FAS. So it generates the same DF for all the data. So the 0.01, 0.005, 0.025, the same group. It goes through the DF is about 0.0030. And if we have the 0.02, 0.01, 0.005 dt, we padding about like 40 minutes and calculate the FAS. So in the output file of the FAS, we have two groups of DF. One group is 0.0030, and the other group is 0.0038. So we only have two DF in the output file. And this makes like a huge data, and computation time increases. And the solution we did is that spend the time. So that we spend the time with the computation with the interns, and also the purchase the data server. So that is the solution, but it works very well now. Okay, so the yes. So I saw the database overview and challenge and solution in data processing covered in this presentation. So I close my presentation to acknowledgement. So data processing, the Walt and Bob and Christine and Chris Kramer and Dave and Brian and Tim and Albert worked on this development of the peer code now we are using. And Olga is also helpful for the windowing studies. And also I really want to say thank you for the many interns, like Shifat and Saha. We are working together now. And also from the last summer, the 1 to 4 interns worked on this NGA-East data processing. So we are in total like 7 people, including me, 6 interns and 1 including me, 7 people worked on data processing for NGA-East data. That's it.
Thank you, Tada. Good. Is there a quick question, a clarification for Tada before we talk about metadata? Tada, hero.
How many thousands of frequency you have in Fourier spectra?
So it goes a lot. Like yes,
a lot.
I think like 6,000 or more. Like
yeah.
It goes like to the Nike DF, Nike's frequency divided by DF. That's the number of the points in the output.
50 divided by 0.0003 or so. Yeah.
Yeah.
Okay. Thank you, Tada. What? Oh, Vladimir.
Vladimir Greiser, NRC. A short question, maybe I missed. What is sync interpolation? Can you just say a few words, please?
Yes. So sync interpolation is done in the frequency domains. So first we calculate the FAS, and we have Nike's frequencies, and padding the zero amplitude above the Nike's frequency to get the new Nike's frequencies, and come back to the time domain. And it put the interpolations in the time domain. So what we can do is like a two-point interpolations, 4-point interpolations, 8-point interpolations, always the power of the 2. So we can only do by using FAS, FFT. So always got two power of the 2 the interpolations for the sync interpolations.
We can send you a reference if you want. It's documented somewhere. Oh, in the paper I have with Dave, we re-documented public knowledge. That didn't sound right. Okay. Bob Young, thank you, Tada. It's going to go over magnitude and distance metadata for the flat file.
So, does mouse work? So I'm have a brief talk on the NGA-East database metadata for the source metadata and the distance calculations. So 2 questions from the TI team. How were the event source data established for the NGA-East database, and how can we address and quantify uncertainty in magnitude, focal depth, and mechanism? So in terms of the metadata for the events, the basic inputs are epicentral location and earthquake depth. Those are one of the first 2 parameters. The epicentral locations were taken If there were special studies for the individual earthquakes, we used that published information for the locations. Otherwise, they were taken from the catalogs, either ANSS for the U.S. or NRCan for Canada. Earthquake depth was taken from moment tensor solutions if depths were given. Otherwise, they were taken from a special study on the events if that existed. Otherwise, they were taken from the catalogs. So basically, we have a flat file, a new spreadsheet for the source files with lists of data sources. Earthquake magnitudes. So earthquake magnitudes were computed from seismic moment using Hanks and Kanamori and are defined in terms of bold M, not MW. So they're defined by this equation here. And the way they were calculated was I gathered all the available moment estimates from the literature and from Bob Herman's MAGIC website, and additional data that was provided by both Jack Boatwright and Allison Bent, which is unpublished at this point, I assume, on estimates of the seismic moments of events. And we put all of those into the a spreadsheet, and then we calculate from each moment estimate the magnitude, and we average the magnitudes. And that's the magnitude that's in the flat file presently. If there were no moment estimates for the events, then we use the relationships that are in New Reg 2115 to estimate moment magnitude from other size measures. And this typically applied to a few small events, typically below magnitude 3. Focal mechanisms were taken from the SLU website or from published literature on the events. And for many events, Bob Herman's site gives a preferred set of planes, so we took that single set of planes. But if other sites often just list both focal planes, and so we've used both focal planes. So that's basically the way the metadata was put together for the events that are in the flat file now, and that's being reviewed at the moment under Christine's fabulous management. No? So any brief questions on that part?
We can't hear you.
Was there any inconsistency between your new magnitude and what you did for EPRI?
There may be some differences that I found more assessments for a few events. In terms of earthquake recurrence, it should be immaterial because the recurrence is all done with bin data, so small differences in the magnitude shouldn't make that much difference. So there may be, if you go to the NGA, the 2115 database lists expected moment magnitude, which accounts for the uncertainty in the estimate. So it's adjusted magnitudes for the purpose of recurrence calculations, where these are average magnitudes from the reported moment. So they're not exactly the apples and oranges. But in terms of the recurrence calculations, these small differences shouldn't have any impact.
John Stewart. So the simulation, my question pertains to your second bullet here.
We haven't got there yet. I haven't talked about that part yet.
Oh, I thought you did.
No.
Okay, well then I'll hold off.
Okay, so I think it's time to talk about that.
The next part I was asked to talk about was the distance calculations that are in the flat file, or in some version of the flat file. So the process was that we are interested in using distance measures that are typically used in engineering application, which are either joiner bore distance or rupture distance for most applications of hazard calculation. And for most of the events, what we have is an epicenter and a hypocentral depth. So for 4 earthquakes in the flat file, we have rupture models that have been used, developed for those, and we can calculate directly from those rupture models the distance measures we need. And they are the 1985 Nahanni earthquake, which we are taking directly from NGA West 2 calculations, and then the Saguenay earthquake, the Rivière-du-Loup earthquake, and the 2011 mineral earthquake all have finite fault models that are being used for the simulation and for the validation, so we calculate distance measures directly to those finite fault models. For the remaining earthquakes, we have used the simulation process that was developed in NGA West and NGA West 2 to estimate our rupture and our JB. So the basic process used for that calculation is for a given hypocenter, we simulate 101 possible rupture surfaces that could be associated with that hypocentral location. We simulate the rupture area using a relationship developed by Paul Somerville specifically for NGA-East, given here. We simulate the aspect ratio of the rupture, the length to width ratio, the location of the hypocenter along strike, the location of the hypocenter down dip, using relationships that Brian and I developed as a part of NGA West 1, and they're published in our Appendix B of our peer report. That basically allows us then to, for a simulation, place an area of a certain dimension, length, and width on the hypocenter. For the terms of the orientation, if we have a focal mechanism with a preferred set of planes, then that allows us to orient that rupture in space in terms of dip and azimuth. If no preferred plane was given, we then randomly select for each simulation one of the 2 planes. And for those events that have no, especially very small events where we don't have mechanisms, we then selected the style of faulting from basically where it was. If we were up in the northeast, we typically see reverse events, so we assumed it was reverse. If we're down near in the vicinity of New Madrid, there's a lot of strike slip. We assumed strike slip, and then we set the dip to a expected dip for the different type of mechanisms. And we assumed a random orientation. I have this slide in twice. I guess I do. So then once we have that, we construct a pseudo grid of sites around this event, evenly distributed over a distance range of 0 to 300 kilometers. When we first did this process in NGA West 1, we used the actual sites, but that then, of course, if you have a new site, then you have to repeat the process. So the method that we evolved in the NGA West 2 was to use a pseudo grid so that we could come up with a single orientation. If we had new sites, we would just use that orientation to calculate distance. And it doesn't bias us directly towards where the actual recordings were. So for each simulation, we calculate the rupture distance to that pseudo site, to the grid of pseudo sites for each site. We then, across the 101 simulations, we calculate the median distance for each site across the 100 simulations, and then we find the single simulation that minimized the square difference between the distance for that simulation and the median distance for all sites. And that's the selected rupture model for that event, and then we calculate the distance to the actual sites from that simulation. So that's the basic process that we use for calculating distance. John. And for most of these events, it's pretty minimal adjustment. So the events are pretty small, and so it's a very minor, I think, minor adjustment, which removes the bias of the fact we don't want to use hypocenter or epicenter, but the details of it are not really critical because these events are so small. So then we get to metadata uncertainties. So on the left of this figure is the standard deviation of magnitudes in the flat file from the range of moment estimates that I was able to gather from the literature. And you can see for magnitudes above about 4, they're typically the standard deviation and estimated magnitude across the range of moments is typically like 0.1. So I don't think that we're going to get moment estimates that would resolve magnitudes, moment magnitudes, to be any better than about 0.05 or 0.1 units, just because of the differences in the way people calculate them. Unless we come up with an agreed upon, very standard, exact way to calculate it with this source model, with this velocity model, we're just going to see differences on this order in magnitude. But they're much smaller than the red line here shows the uncertainty in converting from another magnitude scale. And this is typically magnitude, on the order of 0.25 is about the best you can do in terms of converting from MB or MBLG or duration magnitude or so forth. So we're typically looking at smaller errors in magnitude around 0.1 or less. The other question that was asked about was the mechanism, and the mechanism we dealt with just by randomly selected if we don't have a preferred plane in the simulation process. The third one is the effect of depth, and depths are not terrifically well constrained in the East, and we can have significant uncertainties between different reported events, magnitude depths, and I noticed in reviewing this, typically often the moment tensor depth estimates, which comes from a variety of modeling, versus the catalog depths could have significant differences on the order of 5 kilometers or so. So if we consider a earthquake that's at say anomaly at a depth of 10 kilometers, what is the effect of plus or minus 5 kilometer uncertainty in that depth on the estimate of distance? And so that's what the plot on the right shows, is the red and the blue curves basically are the range in rupture depth you would get as a % difference in the rupture depth, and the rupture distance as a function of 5 kilometer uncertainty on the rupture depth. And you can see it gets very large if you're in close, and then as you get to 100 kilometers, it's basically irrelevant. So we would have, due to uncertainty of depth, we would have large uncertainty in the distances for very close distances for small events. Where we have also, just to show as an example, the green circles is down there, it says ignore vertical scale. They were just shown on here just to show the distribution of data. So we don't have a lot of data in that distance range. And as Norm talked about this morning, we probably need to put some kind of constraints on the behavior in that distance range. So there is uncertainty. There is probably a large amount of uncertainty in that data, but we may be driving the answer based on priors as opposed to actual fitting individual small earthquakes. So again, the uncertainty is greatest at the distance range where we have the data are the sparsest. There are ways of dealing with uncertainty in the input data that can be explored as a part of this evaluation to see whether they matter. One is simulation. We can simulate data sets and see how that affects by just sampling out of the data set with the errors and seeing how that affects our fits, given what we're going to do for however we're going to constrain those fits in close. There are approaches that have been postulated about how to deal with uncertainty in the regression parameters in fitting nonlinear models. One approach, which is basically, which I illustrate here, is that you basically take your data set, you fit the parameters with some simulation to see what the uncertainty is, and you obtain a mean parameter with the existing uncertainty, and then you basically expand the uncertainty and resample and refit, and you see how a certain parameter trends as the error increases, and then you back extrapolate to 0 error to see where that parameter might be if the error was 0. That's some ways that have been explored for dealing with uncertainty in the metadata or the input data. And we could certainly try to do that, or it may be that our choice of priors on that distance term is going to be more important than the uncertainty in the data. And then a few references, mostly for the magnitudes.
Thank you. Any question for Bob on this? Thank Thank you, Bob. So I think we're going to go online and unmute. Oh, yes.
Real simple one. Walter Mooney, USGS. How many earthquakes do you have, and what's the time, in the catalog? You have a...
There are 95 earthquakes in the catalog, or 96. There's a few, I think there's a couple of very old ones. I'm not sure we're using much data from them because of the instrumentation, so it's primarily post-1985, mostly post-1995.
And the last earthquake, the most recent event?
Mineral? Aftershock? Oklahoma, into 2011.
So I guess the obvious question is whether or not the other, 2011 to the present will be added, or it's done. Okay, thank you.
We have to stop and make a model. So it's going to be NGA-East 2. We're going to add more data. Oops. Okay, so Joseph, are you there?
Yes, I am. Can you hear me? I'm here. Can you hear me there?
I need the mic back for a second.
Can I be heard at the meeting? I can't hear anything from anyone there, if I can.
Joseph, can you hear me?
I can hear you now, Christine, yes?
Okay, so we cannot both talk at the same time, but
okay.
Please share your screen and then start your presentation. And if we don't hear you, well, we'll let you know. But
I am currently sharing my, yes.
Okay, thank you very much.
I am currently sharing my screen. Can it be seen?
Joseph, we don't see your slides. You have to do share my screen. Perfect. Thank you.
There's some delay. Can you see my screen now, Christine?
We can see it. If you put it in presentation mode, we'll see it beautifully.
Wait, you see it not in presentation mode?
I don't see a presentation. I see you're working on your slides. Are they done?
Yeah, my slides are done, I promise.
Oh, I'm teasing you. I think you have to remove the presenter view. Huh?
Christine, which screen can you see?
Okay, we can see it, so we'll just live with it, but I cannot make it bigger than this. I think it's because you're in presenter mode, but I don't see where that is.
Okay, you were...
Yes, perfect. Thank you.
Okay, I wasn't...
Go ahead.
Was sharing the wrong screen, apparently. All right, I apologize for that. I am Joseph Harmon. I'm presenting for Professor Youssef Hashash, who is experiencing some travel delays, and I will be talking about the assignment of VS30 to locations in the station in the station database. So just to walk through this, I'm going to talk a little bit about what the geotechnical working group has contributed to the station database. I'm going to discuss the sources for VS30, and then go into the proxy-based estimations of VS30 that we have, and then go into assignment of VS30 and sigma LNV. So the way that we approach this in the geotechnical working group is very similar to the approach that was taken for the NGA West 2 site database, as cited here. However, some important differences: the NGA-East station database does not include basin depth parameters or models or any regional considerations. So there are 1375 stations in the station database, and the primary geotechnical working group contribution is in the measured VS30, assignment of VS30 by the various proxy methods that we have, and then coming up with the preferred VS30 and sigma LNV estimates. So the sources of VS30 that we have a variety of different sources, pulling together measurements wherever we can and assigning them to stations, and this is our distribution of measurements. One of the important things to note is that only 6% of our sites have VS30 measurements, which forces us to rely on proxies to come up with the remaining measurements. So the proxies that we examined were geology, which was developed for NGA-East in Kotke et al. 2012, slope, terrain, the hybrid slope geology method by Thompson and Silva, and then also the P-wave seismogram method, which is a modification of Nian Somerville's method, which we have, I believe, in publication right now. So this is a summary of all of the proxy-based estimations of VS30 at all of our sites, shown with the measurements over here. And it's important to note that in the categories of slope and terrain, we have a very limited range of the estimated values of VS30. So our basis for comparison of this is on the residual of VS30. The residual at any site I is taken as the ln VS30 minus the estimated VS30 from the proxy. So our model bias is mu LNV, and then the standard deviation of the residuals is sigma LNV. So the steps that we took to assign VS30 are as follows. So we walk through this list, and as soon as one of the conditions are met, we assign VS30 to the station from those conditions. So starting at 0 up at the top, if a station has a known VS30 measurement, we assign that VS30 measurement to the station as the preferred VS30. The next step is assigning VS30 if the station is on a known site condition, and measurements of that site condition in the area. This is based primarily on hopefully site visits and also geologist recommendations from someone who has visited the site or knows what the site is founded on. Then we move into codes 2 and 3, where we assign VS30 based on P-wave seismogram first, if we have estimates above 760 meters per second, and then the hybrid slope geology method if we have a predicted VS30 of greater than 760 meters per second. This was done because the two methods we have that we believe most reliably predict high VS30s that might be more representative of site condition are proxies from our P-wave seismogram method and the hybrid slope geology method, which has been calibrated to site conditions in the east. If we do not have that condition met, if we have all of the estimates available at a site, we weight by the variance. If we have multiple estimates of P-wave seismogram at a site, and then finally, if we don't have estimates of P-wave seismogram, we use the remaining proxies and weight, and we use a weight of the remaining proxies. So these are the relative weights for codes 4 and 5. So code 4, if we have the P-wave, we use these weights, which is the greatest contribution of the weights come from the geology and P-wave. P-wave because the standard deviation is fairly low, and the geology also has a relatively high weight, and that is partially artificial because many of the measurements that were used in development of our geology proxy are also measurements that are included in the database. And then for code 5, where we don't have a seismogram recording to be able to do our P-wave method, or we don't have multiple seismogram recordings, geology gets the highest weight, and then the other proxy methods have lower weights. There are some locations where we have missing data, and we handle that simply by reweighting such that the sum of the proxy weights for that site is 1. So for example, if we are missing slope and hybrid at a site, we reweight geology and terrain by the variance such that we can end up with a new weight of unity. The fewest estimates that we have by our proxy methods are P-wave. And that's because we need multiple ground motion recordings at that station in order to be able to estimate VS30. And then there are, for the hybrid slope and geology, all of the sites have proxies available, and for terrain, some of our sites are beyond the resolution of the mapping that was done to come up with terrain classifications, and so no proxy is available for some of those sites. Our weighting scheme for standard deviation follows a very similar pattern as our weighting scheme on the VS30. For code 0 sites, we assign a sigma LNV of 0.1. This is judgment and based on the NGA West 2 recommendations. For the sites where we have known site condition from a visit or geology and measurements in similar geologic condition, we assign a sigma LNV of 0.3. This value is purely judgment based. For codes 2 and 3, we assign sigma LNV from our residuals analysis for P-wave for code 2 and for hybrid for code 3. And then for codes 4 and 5, we weight the sigma LNV the same as we weight our VS30. So what this ends up looking like for the stations in our database, this is the distribution of the recommended values of VS30. This spike at 2000 is due to sites that are known to be founded on rock. In particular in Canada, there's a map of this in just a moment. And then this is the recommended sigma LNV that gets assigned to the stations. This is distribution of VS30 throughout the central and eastern U.S. at our locations. And you'll notice the values of 2000 are mostly in Canada, and at those locations, those are assigned by knowing that the site is founded on rock. And then this is our distribution of code assignment. So how this compares to our measurements and the number of times that we have assigned these measurements is shown here. So the top in blue here, in I guess teal, is the measurement of VS30 is our distribution of measured VS30, and then in the bottom here in the darker blue is the estimated VS30, the recommended value of VS30. So just a summary, the station VS30 measurements are the various proxies are evaluated and then applied to stations to come up with our preferred VS30 and sigma LNV estimates. Some acknowledgments for those who have helped with the various proxies and coming up with our database of information. In particular, MRCE for development of the, in their assistance in developing the geology method, and then our references.
Okay. Thank you so much, Joseph. Can you still hear me?
Yes, I can hear you, Christine.
Okay, thank you. So I'm sorry, were you done or did I cut you off?
Yes, I'm finished.
Okay. Is there a specific question for Joseph on the VS30 assignment? So Walter Mooney.
Hi, Joseph. Walter Mooney from USGS. It seems you have an awful lot of code 5 measurements. So, let's locations, code assignment. Yeah, in the central U.S., a lot of code 5, very few. Is it just it's just the way the image looks, or am I? Is it a visual thing, or is it really mostly code 5?
It's mostly code 5. So if you look here, this is our distribution of code assignment over here on the right. So it is vastly code 5.
Yeah, can you just recap, if you go over the map and just go show what 0, just in your own words? 0 is a measurement and...
Okay, so 0 is a measurement, which is the darkest red values like what we have in here and down here. Code 1 is assignment based on site visit and measurements on known geology, which we have mostly up here in Canada. Codes 2 and 3 are assignment by the P-wave method if predicted VS30 is greater than 760, and we have a yellow one here, and then the teal color, like we have scattered throughout here, is the hybrid slope geology method. Code 4 is where we have all available proxies, including our P-wave estimates, like we have here in Oklahoma. And then code 5 is where we do not have enough estimates we do not have seismogram recordings or enough seismogram recordings to use our P-wave method and rely on the combination of geology, hybrid slope geology, terrain, and slope methods. And that's the darkest blue, which is shown throughout the Great Plains region here.
Thank you, Joseph. Gail has a question for you, and then Ralph.
So would it be fair to summarize that then by saying that as we go from 0 to 5, we're basically going from known to sketchy?
That would be correct.
Sketchy is a technical term for the TI team to use.
Joseph, this is Ralph Archuleta. So it looks as if this is what you used when the TA array was basically centered in this part of the country. It's now moved completely to the East Coast. So are you looking then at the seismology aspects of this as for as the TA array has now moved across all the way to the East Coast?
Oh, we have not looked at that. The method that we've undertaken is only assigning to the locations that are in the station database that was provided to us, which only includes these locations. So
this shows the status of the stations in the NGA-East final database when we closed it on December 2011. NGA-East 2, we're going to have better, and hopefully we'll have better sensors than just a TA array, and we'll have site measurements and all these beautiful things if we start now.
Okay, Walter Mooney again. So I guess an obvious question is, if you're using code 5 and you have an estimate described by Gail as sketchy, and then you go out and you actually measure it in the field to see how you're doing, I mean, how good are these 5s? I mean, has anyone gone out and measured a few of them and seen whether or not you're right on anyway, or how good are the 5s?
Well, I can show you at the sites where we have measurements. This is the mean and standard deviation on the residual for those locations. So in our database, we only have 84 locations where we have measurements. And at those 84 locations, for the Code 5 assignment, we have geology, terrain, slope, and then the hybrid slope geology method. So I guess this is the closest I can give as an answer based on the information I have in the presentation. If someone else has more of an idea, they are free to weigh in, I guess.
So I think what Walter's really asking is, like, if you apply those rules blindly to sites where you have measurements, how good are you? I know you've done that for the P-wave method in a way, right? You did check with measurements, or? I'm looking at John Stewart, and he's nodding, and he's saying yes. Huh? He was, and then he looked away, and he nodded. Yeah. He can turn and nod at the same time. He's amazing. He was my advisor, of course. Okay. It depends.
Yeah, so we haven't done the specific thing that you're asking, where we make an estimate before and then we go make a measurement later and then compare. Okay, so that precise sequence hasn't happened here. But these sigmas are essentially the answer to your question, and those are huge. Okay, 0.5, 0.6, those are very, very large. And I say that, because we've looked at those sigmas elsewhere, like for NGA West, and those are big too, but they're smaller than these. Okay, so that tells you that there's a tremendous amount of scatter in VS30, more in the east than in active crustal regions.
Two questions about those mu's and sigmas. First question is, do you bias correct the estimate? Do you remove the bias, the mu term, when you're estimating the numbers? And second, when you look at those sigmas, which are large, have you looked at correlation? So, for example, if the residual for one method is positive, is it negative on the other, and so on? Because if they were independent, it would be nice, because then the combined estimate will have a much lower uncertainty. But if they are dependent, then it doesn't help you.
We have not used any bias correction on the application of our proxies. So the methods that have, you'll notice the geology method that we have, which was developed from largely these measurements and for NGA-East, has a very low mean. And part of that is because that method was bias corrected for the data set we had at the time. This data set includes a few extra points. So now we have a slight bias in our mean. But as far as the other methods that we have, the terrain, the slope, and the hybrid method, we did not bias correct for our data set. We applied the proxy as they appeared in literature to these sites.
And second, do you look at the correlation of the epsilons?
We did not, no.
Of the errors, okay.
Okay, thank you. So if there's no more specific questions for Joseph, oh, yes? Following the rules. Okay, so if there's no more specific question for Joseph, we'll mute him and turn off the microphone. Is that all for Joseph? Because there's a big sound. Okay, thank you very much, Joseph, for doing that. And we can all say hi to Youssef Ashash, who says he's listening to us from 38,000 feet. And you can, turn down. Thank you so much. Okay. Yeah, you can bring that. So we have a little bit of time to discuss some of the database issues or things that were unclear. So let me say this, then for all of the, again, our focus for NGA-East, because we're focusing on horizontal ground motions, our flat file contains only records for which we have at least a pair of horizontal, and if there's a vertical, it's been processed and it's available also. Okay, so we focus on that. Given that, for all of those entries, 9,576 or so, we have, for all of those, a magnitude definition, the distances provided by the process of simulations that Bob discussed, and we have a VS30 assessment for each of the records. And then, of course, usable frequency ranges, the bandwidth of the microseisms if they were detected during processing, ROD 50. So, new flat file. Are there any questions or clarifications on the database? We have a little bit of time. John Ake?
Thank you, Christine. Going back to Bob's presentation a couple minutes ago, and maybe ask Bob to just go over a little, in perhaps a tiny bit more detail. Right at the end, he mentioned that there would be looking at the trade-off of errors in the metadata versus the importance of using a strong prior. If you could you maybe discuss that in just a tiny bit more detail? I'm not sure I completely understood where you were going with that, Bob.
So yes, I have a microphone. So you were talking about this, basically I was discussing this slide on the right. So as Norm talked this morning, he showed examples of fitting the data and how if you adjusted different parameters, basically the fictitious depth parameter, how that should be established, that if you just fit the data itself, then you would get one answer. Or if you impose, and it was being controlled largely by the data at large distance where most of the data is, and so errors, so it really depends on how that fit to the data is at close distances, and whether that's controlling the fit or it's the values at large distance that are controlling the fit. And if you put priors in, which are based on some other constraints, then that would perhaps limit the variability in that estimate in the data range where we have limited data. So my point was that this large uncertainty in distance occurs in the same place. So that perhaps the solution is not to go out and go back and read all the records from these events and refine the depth measurements, which I'm sure Joseph would be happy to do. But perhaps that we just have to live with the fact that the data we have is sparse in that region and we need other information to constrain it. That's what I was attempting to say off the cuff, as it were. Like,
Okay, any other questions, concerns? Okay, I see Gabe and Stuart. You're ready.
I have a mic, so can I go? My question's about components. So the flat file's based on ROT50. Is that for Fourier amplitude also?
So Fourier amplitudes, we're going to use, no, that's the flat file right now that is publicly available is ROT50. We generate a separate flat file for FAS, and that one is based on FAS squared also. So with, which version? So Justin, when you prepare the FAS file we're working at, it's just FAS, right? Fourier amplitude. It's not squared. Yeah, just
so that's
FAS.
the Fourier amplitude of the as recorded?
Two components is the sum, right? Vector sum.
So you do
yes, which is a vector sum.
You take the components as recorded?
Okay, let's have, I'm going to let Justin answer.
It's the square root of the average mean power, not a vector sum.
Yes.
You square them, then you add them, right? And then you square root. Okay. 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 Right.
And the them,
okay.
You use the word them. That means the two as recorded horizontal components. Yeah.
One question about the distant data. And this is something I noticed, or many people noticed on the Phillips paper on Western T8 array data. If you look at the data as a function of distance, it becomes almost horizontal, around 500 kilometers. Is that an issue here? Have people done any kind of cross-checking of those data? Because there may be something, again, some of the data are strange outliers. Yeah, in the Phillips data, if you look at, they have a figure of the data, and they do it in Fourier amplitude as a function of distance. And at some point around 500 kilometers, it almost becomes horizontal. It's a broad cloud of data. It's almost horizontal. There's almost no more attenuation. And I just wonder, flat to distance, exactly. At least the mean trend by eye. And the question is, well, more maybe a caution that should be checked and make sure that that's not happening. It probably is not happening. I think the data collection effort was a lot more crude, and that may be the reason.
I can comment on that because in my experience, almost every single data set has that problem. You won't get rid of it by signal to noise because it's not that simple. It's basically an amplitude problem, and when you start getting down to the amplitude level at which the instruments are capable of faithfully recording, and it's a frequency dependent thing, then you will see this flattening of amplitudes, and you see it even in really good databases like NGA-West 2. If you look at that carefully and plot it, you'll see at the lower frequencies, when you get out to large distances, for the smaller magnitudes, you get this flattening, and it introduces a bias, and I think it's there in just about almost every single database you look at, and I would be really surprised if it isn't in this database.
Yeah, it is a kind of a preferential sample. You're only catching the big ones. And I was going to say that then that needs to be taken into account in the fitting. That's flattening. And it's a cloud, exactly. But yeah, horizontal. Yeah, exactly. And part of the problem is you're getting more and more records because, again, your data size is increasing as proportional to R, to distance. So it needs to be taken into account in the fitting.
Yeah, it's an advantage of looking visually at data in magnitude, distance ranges for each frequency, and making sure that you're not building in a bias for effects like that don't seem to be very easy to find with traditional filters that we use, like signal to noise.
Jeff Kimball, resource expert question. I guess the VS30 assignment, the impact it has is going to be in the correcting the data. And I guess my question is, looking at the map, there's a whole chunk of upper Midwestern data that is assigned VS30 of about 300. So the site correction for all those sites is essentially going to be a deep soil site correction. It's a question. And those are all on very thick Paleozoic rock sections.
So I think I missed it this morning, but Norm has shown plots of, okay, there's different ways to get at that, right? We can take the site, the delta S2S out of there as well, right, for when we have multiple recordings at a given station. And by that we can take away what was left that was not treated right. But the first thing we want to do is take the VS30s themselves and look at the amplification and see what it looks like. And if we see that some are miscategorized, I think you summarized this morning. I was doing something else, but I heard you talk about it, the background. And why don't you summarize?
We are, it gets a little convoluted when we're trying to keep this all straight. But we're looking at significant errors in the VS30 estimates, first of all. So we think a lot of the sites are misclassified. This is part of what we were talking about in the large variability. You know, the predictor isn't that robust, and when we use that predictor, we find some sites are not being classified right. The way Walter said how many are incorrect, the only way that we can get at that right now is looking at the ground motion as a check, right? So it's circular, but if you use that check, a bunch of them pop out as these don't look at all like it's just a random variation within the category. It looks like we have the thing classified wrong. So when their average terms look like the inverse of a site response, you go, I probably have a soil site that I called a rock site. So first, so what do we do with that? And it's not a small piece of the data, it's a big hunk. That's why our variance comes crashing down so much between a normal phi term or within event variability or the single station within variability. It is so much smaller because we have got a lot of, I think, errors in there. I think it is not just, it's more variable in the East for a given VS30. They're misclassified. So now what do we do? So one way to treat that is to push the problem, kick the can down the road, right? And I'm going to say, let's take out the site terms. So when I have enough data, I can actually estimate the site term and I say, all right, you misclassified it, but I'm going to correct for it in the regression. So now at least I'm getting the right magnitude and distance scaling if there's not a correlation of magnitude and distance to that site. Okay, so that's the big if. So if you can get yourself a subset of data where the sites are measured over at least a range of distances, then we won't trade off between the site term and the distance scaling. But let's say we can do that, all right? And I've now corrected them. what am I going to do? Because now I have a ground motion model relative to something. I'm not sure what that something is because the VS30s were wrong, let's say. So it's relative to whatever the average is of that data set, and I'm not sure what the average condition is. Okay, so that's what I say, you kick the can down the road. Now, the way we can try to deal with that is then separate the data into the subsets where we think we're getting, let's say, reasonable or reliable VS30s, and those that we think are questionable. The ones that are questionable, I let them get their own average, and I don't care what it is because I'm going to throw it away. But I use them to help me control the distance and magnitude scaling. The ones that are reliable, I can now say, what is the average VS30 of the reliable ones? Okay? So, or maybe it's 400 or something. And an average is much more robust than what is an individual one. So now I can say my derived ground motion model is anchored at 400 meters per second, or it's anchored at 300 meters per second. Then I can go to the geotext and say, tell me how to correct that back to 3,000. So I can now adjust my ground motion model back to 3,000. And this is the phase that we need to get through. If we don't do this, I think it's trying to deal with this empirical data with what looks like pervasive or massive site correction errors is a huge problem, or site classification errors. Is that making sense? It sounds like we're going in circles. It's a bit of circles because we're saying we're going to declare things that are not following our preconceived idea of how site scaling should be as unusual, and we'll push them, or unreliable, and push them to the side. You're talking too long to not have a microphone.
Sorry, bad habit. You guys will probably touch on this in the upcoming sessions, but it sort of gets to what Jeff was talking about. Of those sites that fall in that site classification 4 or 5, which are the sketchier sites, what fraction of those do we think we have enough data to do the single station?
So I asked Justin to do that right now. So do you have them? Not yet. So he's working on those. So
in real time.
Let's do it for tomorrow at least. We'll get those numbers because I think that's the best way to look at it. We can see what one is, how many sites are in there, what is the variance of those site terms. It should be getting really big in the class 5, and I hope it's a lot smaller in class 1 or 2, right? Or some. So that's sort of the end check of does the whole thing make sense. Okay, but that's believing that the ground motion itself is a predictor of the site response, and fundamentally we shouldn't be having that large of a difference of the ground motion for a given site category than what we would expect from well-characterized sites. So we'll get to that, but I think that's a piece that we need to demonstrate. How many of them? So the questions are numbers of sites with, by a histogram of sites per, or recordings per site by this classification scheme, and then the standard deviation of the phi SS's by classification, or the phi S2S terms, right? So then we can see what's going on. So our expectation is that phi S2S term gets bigger and bigger as you move into class 5. And then one of our questions is, do we sort of impose our answer on the problem by saying we're only going to use those sites where the shape of those site terms is relatively flat? We'll put in some tolerance and say those are the ones we're going to believe are more robust and center our model on those. I would not even downweight them. I put them off and give them their own constant. I don't care what that constant is, but you put it into 2 categories. You're developing a regression, and you have a constant in front for your well-classified sites, and you have a different constant for the other ones, and you just throw that one away. The constant that goes with it, right? So the data are distributed. There's they'll contribute to the variability. We might want to downweight that site, but really their site term is computed And what I'm worried about is the influence of that site term on the median. But if I give them their own median, it gets thrown out, and it doesn't control the answer.
And we might need to put in a variance difference for them too in the regression.
That would make sense to have, so it's essentially a separate random effect with a different variance for that class, because we don't want it messing up or influencing the estimates for the reliable class. I'm thinking of two groupings of the site terms, reliable and unreliable, okay, and the unreliable ones are used only to help borrow strength for their scaling constraint on magnitude and distance scaling, with the caveat of dealing with the correlation, so we're not mapping that. And the other one is going to also inform us of where the model is centered. Okay, then we can hand that information to the geotechs and say, we're centered on this, adjust it for us to 3,000, and then we apply that adjustment at the end. Is that making sense?
So one question that we actually asked, we retracted it, is what is that average? But I think it's going to come out of that process, because we have to see what is the distribution of sites that look like they behave like what we expect in terms of site response. And because we deem they behave correctly or whatever appropriately or it's acceptable, the average VS of those sites is actually our average we need to correct to 3,000. So while Norm is typing up notes on the sigma of reliable and sketchy, any other questions? Walter.
Walter Mooney again from USGS. It was obvious in the map that there was a preponderance of VS30 measurements made in Canada. And I'm just wondering if they have a better way of doing it more quickly, or why are there so many measurements there and fewer south of the border?
It's not really measurements. My color scheme was not as different. It's mostly class 1. That's basically VS30 based on known geology. And in Canada, they try to put the sensors. I'm Canadian. They try to put the sensors on the Grenville. So most of them are not actually category 0 measured. They're kind of inferred from known geology. Some of that comes from Gail's toolbox. The rest comes with talking with people who actually went and picked the stations and their geologists and said, I remember we put that on Grenville, and then based on average velocities expected for the Grenville or Appalachian, where it's more 1,200 instead of 2,000, that's what it appears to be class 0, but it's class 1. It's inferred from known geology.
Yeah, part of those knowns might be optimistic. I mean, some of them really are known, right, because there have been a number of shear wave velocity measurements on sites. But then a lot of them are just because, as Christine mentioned, the practice at the Geological Survey for decades basically has been to site instruments on hard rock. And in the areas where we have lots of earthquakes in eastern Canada, we also have lots of hard rock. And so if you can go out to the site and hit the thing with a hammer and it rings, then it's probably got a shear wave velocity of 2,000 or better.
That's a sketchy assessment of a category 1, but okay. Okay. So, but I mean, really the Geotech Working Group on that did a fabulous job. It was a lot of work also to reconcile all those data from interviews and talking to people and putting this station with reassessing. Since January, they reassessed all the different weights they put to those methods, especially to include that category that was not as well captured before. Okay, are we good? So it looks good. So we're going to shift. Whatever. So I always joke about that. Norm cannot type, I cannot talk. Together we can do something right. Okay, so we're moving on to regionalization, and Gail now is going to summarize the work of Walter Mooney and Martin Chapman and their teams on regionalization, and in terms of their impact to ground motions. They have produced a report that's under editorial review right now. It's almost done. I mean, it's all written. It's just a matter of making sure the documentation is what we want to see in there. And she's really going to focus more on the ground motion aspects of it. Okay.
All right. Thanks, Christine. Well, Norm mentioned this morning that it's his job at this point to take the credit for work that was mostly done by others, and so I'm going to do him one better and appear to take the credit for work that was entirely done by others and I had absolutely nothing to do with whatsoever. And so I'm in the slightly strange position of making a presentation on ground motion regionalization work that was done by Walter Mooney and his group, particularly Jennifer Dreeling. So the overall summary of the ground motion regionalization approach that the TI has adapted is based on a series of analyses and reports that Walter Mooney and his group have prepared. There were some very slight modifications that were made to initial drafts to expand some of the regions to include the regions of Canada, for which we have a lot of data, and the important recorded events and stations there, and also to extend regions slightly offshore to capture things that would otherwise be missed. But by and large, it's basically what Walter Mooney's team came up with. So what's the overall basis for the ground motion regionalization? So it begins with 4 regions that have distinct geologic structure and tectonic history, which are shown in this very simple cartoon here. And then the basic idea was begin with each of these 4 regions of different geology and structure and characterize the representative crustal velocity structure for each region, including also a Q characterization, and then use simulations to explore the effect of the crustal structure and Q on the actual ground motion amplitudes. The reason that this is the approach taken is that it allows one then in the end to come up with ground motion regions for the ground motion prediction equations that are based on statistically significant differences in ground motion. And here this is in comparison to a reference region, which is Central North America, which is in the Mooney report, CNA is the designation for Central North America, which is the largest and most data-rich, in some sense, regions. So just to quickly show you what each of those regions look like. So the reference region for the study that you will see in the coming slides is Central North America, and that's the region outlined here. There's the Appalachian region, which is this region. There's the Atlantic Coastal Plain, which is this region. And then there's the Gulf Coast, Mississippi embayment, which is this region. So those are the 4 regions that we begin with, and there they are again. So the analysis method to go about conducting the regionalization was to analyze and synthesize a very large volume of data on crustal structure. And this map just shows all of the data that was compiled and analyzed by Mooney's group, an incredible number of data points, actually, many thousands of data points, where here the red dots are points at which there's a whole crustal model available of velocity, and then the blue are shallow crustal profiles. And these data records, they're not entirely uniform, but in general what the data records things that would often be included, obviously the latitude and longitude of the measurement point, and then the structure of the entire crust to the extent in which it was known at that point, P-wave velocities, S-wave velocities if they were measured, sediment thickness, thickness of the crystalline crust, and any descriptions of the crustal layering, as well as information on crustal type, tectonic age, experimental details. So this is a very large set of data records that was compiled. And just to give a flavor, an overview of some of those data, this is a map of the thickness of sediments across the entire region. Here is a map of the depth of the moho. Obviously, this is a very important parameter in terms of modeling the effect of crustal structure on attenuation. And so this is a contour map based on that database in which the moho depth is contoured. And then here is another similar contour map in which what we're looking at is the average crustal shear wave velocity in kilometers a second. And all of these maps are available in Mooney's report, and there's also a software package and a database that is available where one will be able to go in and for a particular latitude and longitude query these parameters. So then with this, from this database, velocity profiles were compiled for all of the points for which they're available. And so, for example, for the central North America region, the CNA region, then all of the red dots here would be the basis of the data points from which representative velocity profile for that region would be compiled. And so if you take the data from all of those little red points on the map and you plot the velocity profiles that you get from all those points, you get something like this. So we've got that scatter plot on the left that shows all of these different velocity profiles, and then that's translated into a distribution in a sort of a heat plot format on the right-hand side. So this gives you a good representative profile, which is shown by the red or the central line there. So if you take kind of what is an average or representative profile, that's what it is. And then you also get a good picture of the uncertainty or the variability in that profile from place to place. And of course that variability in the velocity profile is going to map into variability in ground motion attenuation when you move into the simulation domain. So then here's just a summary of those representative seismic velocity depth profiles for the 4 different regions, the central region, the Atlantic, and the Appalachian and the Mississippi embayment, in which we have profile of depth versus both P-wave velocity and S-wave velocity, where the S-wave velocity was calculated assuming a Poisson's ratio of 1.73. And here's what they look like in a plot versus depth. So there's just those 4 regions again, and those are the representative velocity model. And of course, we have to keep in mind, we'll come back to this in a second, that there's going to be in every region variability of that velocity profile from one site to another. But this is just the representative shear wave velocity profile. So in the simulations, one of the things that was done was to consider the impact of alternative crustal models, focusing in particular on the reference region of CNA. And this shows, for example, this shows a box and whisker plot for seismic velocity uncertainties with a box interval of plus or minus 25%, and the whiskers at plus or minus 45%. So showing how from one site to another the velocity profile might vary with depth. And as we'll see in a minute, this has implications for the uncertainty and attenuation. One of the other parameters that was evaluated was how variable is Q across the region. And Q, as I think most of you already know, controls the frequency-dependent anelastic attenuation. It's mostly important in ground motion predictions at large distances and at higher frequencies. And this is an example of a map from one of the studies that they looked at that shows a regionalization of Q naught, which is the value of Q at 1 hertz, across the entire continent, and shows that in some regions in the mid-continent, for example, and in the eastern part of the continent, you may have higher values of Q naught, implying lesser attenuation than in other regions, where as Q is inversely proportional to the anelastic attenuation. So what Mooney's team did was to, rather than try and determine Q in any sort of really fancy or sophisticated way, they did a literature review of Q functions that had been published in each one of the regions, and then they just assigned a median Q value function for every region based on that literature review. And this is just an example of that process for Central North America, where they took a number of Q studies and just drew the median, which I've highlighted in the yellow there. So these are the Q functions that were determined then using this median from the literature review approach for each of those 4 regions, and it also shows you the typical Q value at a reference frequency of 5 Hertz. So 4 different regions. Each one of them has a representative velocity profile. Each one of them has a Q function, and there's also, in greater detail for the central region, an analysis of the variability of that profile with depth and its effect on ground motion. So that brings us to the ground motion synthetic point, or part of the study rather then. So all of these models were used to generate ground motion synthetics using Zoo's frequency wave number code in the frequency band from 0.5 to 20 Hertz. So the regionalization defines the velocity model. That's the kind of the first steps of the process used to calculate the Green's functions. And then those are convolved with a simple triangular source function for magnitude 6. Just a simple reference magnitude approach was taken at several focal depths, 5, 10, 20, and 30 kilometers. And then the response spectra are computed from the synthetic accelerograms, and we can then look at how PSA behaves as a function of distance for the different regions, and we can look at what things are important to the attenuation of PSA. What difference does it make if we have a different crustal profile? What if we vary the velocity in this layer by 25%? What does that do to the attenuation? What happens if we have a deep source? What happens if we have a shallow source? What if we change the Q? What difference does all these things really make to ground motion, because that's what we really care about? So here's just an example of those computations, thousands and thousands of synthetics computed. This shows for different frequencies in the central region for an event at 10 kilometers depth. How does PSA behave for different frequencies, shown by the different colors there. And you can see you've got this kind of slightly jagged curve. Keep in mind this is for a particular representative velocity profile. If you look at alternative velocity models within the central region, that's based on that plot that I showed with the box and whiskers, where you kind of vary the velocity profile. You can evaluate what is the representative within region variability that is attributable to variability in the velocity profile, and then you can use that to evaluate other regions against that and determine to what extent the ground motions in those other regions are really different from the central region by virtue of the fact that the other regions have a slightly different velocity structure. So you can see that in the central region here, this is plotted for 5 Hertz PSA, just varying the velocity model. You can see that you get quite a lot of scatter, even for a fixed focal depth, in what would be the predicted synthetic ground motion from varying the velocity structure. It can be as much as plus or minus a factor of almost 2 as you move out towards regional distances. So this then becomes a useful tool to evaluate how significantly different are other regions. And there's a lot of plots of this form here, in which what you're looking at in the background is the mean and the standard deviation of the ground motion for the central region, and then according to the different velocity profiles. And then if you have the same amount of variability due to velocity profiles in other regions, such as the Atlantic coastal plain shown here, but a different representative profile, how different is one band from another? So you're comparing not just 2 specific lines where you say, well, this attenuation is different because the how different are the bands? We only really think that the ground motions are different if the bands are significantly different. And so this is a very useful way of looking at it. We're interested in not just the mean, but also its standard deviation. And this shows for one particular frequency band from 0.5 to 1 hertz and one particular focal depth, 10 kilometers. And this is repeated then for different frequency bands, the 5 to 10 hertz band, and also focal depths of 5, 10, 20, and 30 kilometers. And this is just another similar example, comparing in this case the Mississippi embayment to the central model at the same frequency band, but a deeper focal depth. How different are the models? And the overwhelming thing that comes out at looking at these plots is that for most of the regions, the spread of these bands is such that there isn't that much difference in ground motion from one region to another, with one exception, which we'll get to in a minute. So in general, the scheme here is that what we're looking for are differences in ground motion for other regions in comparison to the reference region that are significant. And criteria for being significant generally follow guidelines that EPRI laid out in '93, that we would consider differences in median to be significant at the 95% confidence level, and also that they be greater than 20%. In other words, they might be statistically significant, but if they don't matter because they're so small, then they're not significant. And that criteria should be met for a number of consecutive distances and frequencies having the same polarity. So in other words, if it bounces back and forth, it's not significant. And so the mean, or the key variables rather than in looking at whether something is significant, are the mean and the standard deviation of the ground motions for each region in comparison to that for the reference region. So does the mean PSA for a region fall within the standard deviation for the central region, in a nutshell? So the conclusions of the study are that there are two distinct attenuation groups. Group 1 is the central region, and it also includes the Appalachians in the Atlantic coastal plain because the ground motions are by and large not noticeably different from the central region. And then there's Group 2, which is the Mississippi embayment, Gulf Coast, for which the ground motions are distinctly different from the other region. And so that was kind of the first main conclusion, is that there's two very distinct groups there. And then the other conclusion, which was, I think, very important, is that the seismic velocity structure has more effect regionally than the Q does. So when they looked at what matters, the regional variations of Q didn't make that much difference. The regional velocity structure made more of a difference than Q. And so Walter is probably cringing back there. He can correct anything that I got wrong.
Okay, Walter's happy. Martin?
And
Martin
I will sit down at this point because if there are any questions, Walter is going to answer them.
Okay, so I know we were supposed to have Rob right now, but it seems like it would be pertinent to have discussions and questions and take care of this, and then we come back to Rob right after the break. Unless there's no questions, I mean. Why don't...
So you want to say a few words about your TI final version of region?
Well, the regionalization as we see it now, based on those results, is we have two regions. The Gulf Coast and everything else for attenuation of ground motion.
Maybe the only thing I'll add is that we did all our calculations for on land, assuming everything is on land. So we didn't calculate an earthquake 200 kilometers offshore, at the continental shelf, propagating to the Atlantic coastal plain. So, although that is the larger region, we were using onshore data.
So Ralph Archuleta, so Christine, you said that there are two regions, but then how would you explain then mineral, which showed very definite different distributions if you went east-west versus going sort of up in towards northeast?
Directionality and azimuthal issues are going to be in NGA 2 or 3, but I'll let Martin. Do you want to answer to that, because you've done azimuthal comparisons too?
This is Martin Chavin. In addition to the simulations that Walter's group did, Richard Godby and I looked at some different azimuthal dependence. We extended the simulations out to a distance range, well, same distance range, but for different source receiver azimuths and some different focal depths. And what we found out is that if you have a very bright mid-crustal reflector, like Walter's model for the coastal plain region has, you can get some substantial differences. We found about a factor of 3 for the transverse component for that Atlantic coastal plain, factor 3 greater than for the central U.S. And so in cases where you have that kind of a situation, you can get some substantial differences, substantially greater ground motions. And maybe something like that is taken in the case of the mineral earthquake. That might happen in directions to the northeast from the source up there. The problem is we just don't have enough data to really say that this is a pervasive condition that exists throughout the coastal plain region or not, because that's very sparse data there. So you can come up with these models, these simple layered earth models that can give you synthetics that suggest that you can have some really large regional differences. But at the same time, you have to sit back and say, well, just how well do we know this, and whether or not it's really an extensive crustal difference over a very large region. So it's a lack of data. We just don't know if we have the kinds of velocity contrasts that we see in some of the models. We don't know whether that exists everywhere over, say, the whole Atlantic coastal plain province.
Thank you. Larry had Larry, is this directly on that? Okay, on the same topic.
Ralph, I think your comment is that the mineral earthquake, did you feel it results indicate a northeast amplification, higher, did you feel it reports than going to the northwest? So the answer is, we studied 4 regions and compared 4 regions. What you're discussing now is going from one region to another. So you go from the coastal plain into the Appalachians and into the central United States. So you're traversing. We never examined crossing regional boundaries, which is another effect. As you know, of course, it has structural complexities like a dipping moho, and the crust is varying. Whereas if you're propagating to the northeast within the coastal plain, you're not crossing any boundaries. So I think that it may be a region boundary effect that makes it higher amplitude to the northeast. That's a hypothesis.
Yeah, but in addition to that, there may also be directivity associated with the mineral that causes that focusing to the northeast. I think that's been discussed as well, which is obviously, not going to be captured in these velocity structures.
Yeah, I just want to say that Rufus Ketchings at work gave us a nice seminar where he was looking at that, and my memory was that he thinks it's actually maybe fault zone wave propagation, that there's apparently fault zones heading toward New York City. He doesn't think it's like the lineament of the structure there. So he has an alternative explanation for that as well.
Just a confirmation. It was put up fairly quickly, but since it's the Gulf Coast and everything else, I believe the Gulf Coast outline was equal to what Walter, to to what Martin Chapman did for EPRI 2013, and it's the same boundaries. I'm just trying to confirm that. It looked like it was, but I'm asking that question.
I think so, right? The bottom line was we asked them, if there's no reason to move the boundary, don't move it. So you guys only changed a little thing near Florida, right?
There's a few very minor differences there, but nothing substantial.
Larry, the good news is Martin and I got together at VPI and hammered this out before we went off and made two different models. So you're rest assured they are consistent with the other boundaries. We thought that would be an important thing to do right at the very beginning.
So I think we do need to check all sources of data for regional differences, and one that we haven't been going through is the did you feel it data, for example. And from that data set, are there indications of regional differences in these four zones that we've talked about? I don't know what that data looks like. Have you looked at that, Gail?
Yes, I do know what that data looks like, although I haven't specifically looked at if there are differences you could regionalize. My guess would be I suspect that not that you could pull out because the variability is quite large. But actually I do have all of that data more or less compiled. It probably wouldn't be that difficult to look at whether there's any evidence in the did you feel it data that would refute that assumption. I suspect the answer is no.
John Evans, Geological Survey of Canada. I think the conclusions follow from the assumptions, but I mean, I think the assumption of the assumed Q values that we use probably needs well documentation. Like those median Qs are actually very similar, right? But is that the right way to approach it? Should you be using different Qs and different, like a whole family of different Qs? And were there Q relationships that were not used?
If I try to repeat what you just said, are there Q models that were not used which would have led to a larger difference? Is that correct? So you picked some, but were there other models that were much more different which would have implied a larger change?
Yeah, well, I think Gail showed a map from back here in Mitchell that showed that the eastern and central U.S. was mostly, I think, kind of a dark bluish or reddish color, high Qs. And as you know, there's not much difference between a Q of 900 and a Q of 1200. Q gets significant when you start moving lower to much lower values. I agree with your first point, your point that the assumption led to the conclusion because they were all high Qs. But we simply did a literature search and got everyone's measurement and got a median value based on the field measurements. The analyses based mostly LGQ. So yes, it's the same as Eastern Canada, Central and Eastern Canada. Generally you have pretty high Qs. When we're talking about Q naught. I'm talking about this map here. It's green. It's almost all green and blue, and a lot of values are. Well, this is Q0, 500 and higher. So these values are at 0.5 hertz. They're starting out at 450 at median, but then they're moving up really to pretty high values. So it's pretty high Q. Are you thinking that there are low Q values that, and we're bringing it up to 3,000 meters per second. We're not considering the sedimentary deposits. Our models don't come up to a sedimentary basin. The basin is missing. If it exists, we're bringing it up to 3,000 meters per second for VS.
John Adams, Geological Survey of Canada. what I would say is there's an enormous scatter up there, and you've made quite an assumption in assuming that the median value or some dashed line going through it is actually an appropriate measure for that particular region. Now, it has happened that they've all come out more or less the same, but I think you probably should look at the case that, in fact, differences have been smoothed out by the process.
So I think the way we're going to have to deal with this at this point that we're at is to make sure we sample the cues in a forward sense. We cannot redo that study that took a long time. So that part is done. What the TI team does with it and how we interpret it and how we decide to make sure we capture a variability if it was truly missed, it's really in the forward sense of the simulations or constraints on the models themselves.
If I can make a further comment on that, there definitely will be significant epistemic uncertainty in Q that isn't necessarily represented in this particular study that will be represented in the ground motion simulations. But I suspect that in the end that the epistemic uncertainty in Q is only going to be a significant factor for ground motion at high frequencies and large distances. Other things like the epistemic uncertainty in the geometric spreading model will have much larger practical impact on the ground motion estimates.
And that's regarding that, tomorrow we'll talk about simulations, and Gail's going to do a summary of the Q models that exist for ENA, SINA, the whole thing. And if any is missing there, there's going to be a time to speak because these can be used in a foreign sense. We'll see how we're going to treat epistemic uncertainty tomorrow. But at the very least, the original idea was to use, say, a certain geometrical spreading with the Q published value as kind of an epistemic parameter in the forward model, point source, large distance, where it's going to matter there. But yes, so yeah. Walter? Gabe has been wanting to talk for a while.
And John, one last comment. We made the observation that the velocity structure has a larger effect than Q on the PSAs. And the complete statement in the report says in the first 100 kilometers. So we did qualify that. You know, as you start going out to long distances, then you're talking about a whole other thing because Q begins to play a larger role. Okay, so finally.
Yeah, one comment relates to the regionalization and to the long-distance paths. It may simplify matters to remember that the long-distance paths matter for only 2 or 3, let's say 3 RLMEs, or repeated large magnitude earthquake zones, New Madrid, Charleston, and Charleroi. And so in many ways it's a more restricted problem. You don't have to consider long-distance paths from anywhere to anywhere. You need to consider just a few, is my guess. That may need to be confirmed with sensitivities, but that may help.
Absolutely. Thank you. Any more questions on this or clarifications? So unless we show differently by digging into the data and suddenly a new region pops up, we have 2 regions for the East, for the modeling part. So
one quick question on that issue.
Yes.
Will you consider multiple regions, say, for kappa?
We'll talk, yes. So we didn't bring that back again, but our reference rock and kappa have been determined, right? Reference rock is 3,000 meters per second with a kappa 0.006. But the Gulf Coast we expect to treat differently. And this afternoon, the last talk is going to be Martin Chapman talking about how we can go and change these reference conditions for the Gulf Coast and Mississippi embayment so that the adjustments are not too drastic or need to go too deep to happen. Okay, yes. Rob, do you still want to give your talk before break? It's epistemic on or off, yes or no? Yes, I think so because we have time. Some things go faster, some things go slower. So nobody revolts at the idea of two regions. Good.
Okay, so just get settled here. Robert Graves, member of the TI team. I'm going to make a presentation. Yeah, your microphone's too short. Okay, so I'm going to talk about region or depth dependent of Brune's stress drop. And this is largely based on work that Jack Boatwright has done recently. So I'll provide a summary of his work. And then there's some questions that I'll come back to at the end. I put those out here just to kind of set the tone. So we're going to look at whether the results can be applied throughout the entire Eastern North America, or are they limited to specific geographic region? Are there other explanations for some of the trends we'll see, in particular stress drop increasing with depth? And then touch on some other work that's been done. I do want to point out this box at the bottom. So I'm going to use the term Brune's stress drop. I'm going to try to use that term. But anytime I say stress drop or it's labeled as stress drop on a figure, this is strictly talking about Brune's stress drop, okay? So Gail is asking, can I define what the Brune stress drop is? Oh, using a Brune model. Yeah, sorry. Yeah, stress parameter. And I don't know, I thought that would clarify things if I put that up, but apparently we'll just blaze ahead here. Okay, so Jack and his colleagues have analyzed a number of earthquakes. I think there's over 30 events here that they've looked at. This is north central U.S. and eastern Canada. Magnitude range is 2.6 up to magnitude 5.8. And there's a couple studies, which I have the references there, that Jack has done. Okay, so this is a map that's showing the distribution of these events. Initially, the Boatwright and Seekins work was concentrated up here in eastern Quebec. So these black stars are the events that they looked at. The red stars on this map are the subsequent events that Jack has looked at. There's three broad regions that Jack has defined. So there's this western Quebec seismic zone, which I think Jack also included some of the events in upper New York State, eastern Quebec and New England, and then everything else, basically. So there's some events down in Ohio, the mineral event, and so forth that are kind of just all lumped together. So we're going to, for the purposes of this talk in terms of regionalization, that's what we're looking at. Okay, so here's the ground motion model that was used in doing this analysis. And it basically, these are the observations. It's the Fourier amplitude spectra of the ground velocity. This is a kind of a rather typical expression of the ground motion model. There's some factors in here. The important ones are the geometric spreading, so this is an assumed form It's basically 1 over r within 50 kilometers, and then it goes as a square root of r beyond that. The anelastic attenuation term, and I'll come back to that, the specifics on that, but it is frequency dependent. And then basically what's being solved for is this source spectrum. And then that is the observable, and it's fit then with these corner frequency or the Brune stress drop. Okay, so Q. We just heard some talk about Q, and this is data and analysis that I think was out of Boatwright and Seekins. They analyzed a number of events, and this is the Q function. They found that it provided a good fit to data across the entire set of regions. And it's the Q naught here, 410, is lower than I think that we saw in the previous presentation. And there's a variety of reasons why that could be. It is tied to a specific geometric spreading model, and so there's an inherent trade-off there. In any case, that's the model that has been used for this analysis. So here's just some representative results. These there are 2 events in Quebec, both about the same magnitude, 3.4. The colors, the green and orange, represent all of the observations, and this is, if I have this remember correctly, I think this is a standard deviation of the mean of those observations. And then the heavy line is the fit with a Brune type source with those particular parameters. So the corner frequency and the Brune stress parameter in each case. And you can see here's 2 events, same region, same magnitude, and they have about a factor of 2 different in the Brune stress parameter. So that's just kind of representative of the variability that's inherent to these data. Okay, here's the result for the Saguenay earthquake. So Saguenay is the largest earthquake in this data set. And many of you in the room have looked at these data. These are the parameters. So it has a stress parameter of 419 bars, relatively high within the events that Jack had looked at. I do want to point out that there's features in this observed spectrum that are not fit well by the Brune model, and this is pretty well known. We'll probably come back to this tomorrow or in the next couple days when we start talking about finite fault. So I'm not going to get into those details there, but I just wanted to point that out as a teaser. Okay, so now I'm going to go through a series of plots looking at the variation of stress parameter versus magnitude, and then we'll look as a function of depth. So Western Quebec, here's all the events, the stress parameter on the vertical axis plotted against moment magnitude. And there's, again, a lot of scatter, but there's not really a strong trend as a function of magnitude. Maybe there's a hint of a trend there. Here's the same type of plot for the eastern U.S., some of the events labeled there. This, I would say, is suggestive of a trend, although if you took mineral out of this, then maybe that suggestion would go away. Some of the source, the depth on some of these sources is not all that well constrained, particularly for the very small events. So there's a lot of uncertainty in this. Here is eastern Quebec, magnitude or stress parameter versus magnitude. Again, there's kind of a hint there. I think if I remove Saguenay, then maybe that hint goes away. But the point is that as a function of magnitude, there does not appear to be much of a trend. And if we plot everything together, we basically see a kind of a shotgun. And I think this is something that has already been seen and discussed. So there's not much to suggest that there's any trend as a function of magnitude. Okay, so let's look as a function of source depth. This is Western Quebec. There's actually the source depths are actually kind of tightly bundled, but there's no real suggestion or hint of any trend there. And again, I note here, based on what Jack had said, that the source depths are poorly constrained, so there is that element of uncertainty. Okay, so here's where we actually see a trend, Eastern Quebec. And there is a very clear dependence, at least in terms of this analysis, of the Bruin stress drop on source depth. This is also the only region where there's events that are deeper than 20 kilometers, which would be, if I can get the mouse to that, that's about right here. So even if you took those events out, I think there's still a very strong trend in here suggesting that there's a dependence of stress drop on source depth. If you add in all of the events from all the regions, it certainly diminishes that trend, but I think it's still in there. And in particular, there are studies, I cite as an example here, Hardebeck and Haukson, who noted that in cases where you might expect increasing stress drop with depth, that it doesn't necessarily mean that all the deep events are going to have high stress drops. It really means that the maximum stress drop increases with depth, and that's kind of what you see in this plot. So that is consistent. Okay, so let me try to shed some light on these questions. I'm not going to provide concrete answers to these, but just some observations. So are the results generally applicable to ENA or only to a limited geographic region? So the results do indicate some regional differences in average Bruin stress drop. However, there's relatively few number of events, and there are relatively large uncertainties, particularly with the source depths. So that suggests caution in drawing firm conclusions on this feature. So I think these data are suggesting that there are not regional differences between the median or the average stress drop. Depth dependence is clear in Eastern Quebec, and it seems to be fairly well resolved with this model. And that's true even if you take Saguenay out of the mix. It is obviously an important event because it's the largest and deepest event in the analysis. And as I had noted, the other regions don't have events below 20 kilometers, so trying to delineate that trend is possibly being masked because we just don't have the observations at those deeper source depths. Okay, can these regional or depth variations of Bruin stress drop be explained by other effects? One factor that may strongly affect the results is the use of the constant attenuation model across all of the regions. And this would be most significant for more distant stations at the higher frequencies. And in this analysis, this approach, you're basically mapping those back to get the source spectrum. So it could be significant. And in addition to that, the geometric spreading term, the assumed form, is in a sense tied to that attenuation model. And so it might have a similar effect, although I think it potentially is less significant. It's not clear whether those assumptions are going to have a systematic effect on the results or if it just kind of changes the picture, but the same picture is still there. My last point or bullet here is that I think it would be useful to explore the sensitivity of these particular results in this analysis to the assumed attenuation and geometric spreading models. Okay, some other studies. There have been a number of studies looking at variation of stress parameter versus depth. Here's an example from southeastern Australia. This is work done by Trevor Allen. And he found that there was a step, if I get my mouse to show up here. So this top plot is stress drop versus magnitude, no clear trend. Bottom plot is stress drop versus depth. And his result is that there's about a factor of 2 increase here at about 10 kilometers. Again, fair amount of scatter. Now, you might be able to fit this with a linear trend as well. So it is a similar type of tectonic environment, and he seems to feel that it's pretty clear in the events that he's looked at. There's also work going on with the NGA West data set. This is work done by Anne-Marie Balte and Tom Hanks. They've looked at events in Japan, that's on the top plot, and also the NGA West 2 data set on the whole, and they see a depth dependence of Bruin stress drop in those versus depth in those cases. Now, granted, there's a lot more data and presumably maybe better resolution on the source depths. So I think that's it. Yes, and there's the references.
Are there, so you showed 2 other or 3 regions, let's say, Japan, NGA West, and then Australia, which all had a depth dependence to them. Are there any other regions that show no depth dependence to the stress drop? Because if the East is the only one and it's sparse data, then I'm not as comfortable doing that.
Yeah, that's a good question. I don't know the answer to that. I think maybe we need to look.
This isn't really the answer to the question. It's actually sort of another related question, and it was a question that I think that we raised another time that I had regarding Jack's work, and I don't know whether he's actually yet done it. The conversation that I had with Jack, I really like the idea of an increasing stress drop with depth, and I've looked for one for years and never actually been able to convince myself that it's there. So I was sort of surprised that it came out so strongly in Jack's, because I thought, well, if it's that obvious, how did I miss it? So I went back and I looked at some of those things. So I looked for it in 93. The data was pretty sketchy. I looked for it in 2004. The data was quite a lot better. But when I looked for it in 2004, what I found was not a dependence so much. The most compelling thing that I found was a dependence of the attenuation rate on focal depth. So in other words, if you do a giant inversion and you fit everything with one attenuation model, which is essentially what we're doing here in Jack's study and perhaps in most of the other studies as well, where you do a big inversion, you have a background geometric spreading rate, and then you find the Q and the source. If there is a dependence of the geometric spreading rate, for example, on focal depth, which you would expect as a, you would expect that. Some of the synthetic studies actually have showed that very nicely, that the focal depth affects the attenuation. So if you look at the residuals of the attenuation for earthquakes of different focal depths as a function of distance, the first thing, before you assume that it maps into the source, that you have to find out is whether there's an attenuation residual there that's significant. So in other words, if he looks at his deep events greater than 20 kilometers and plots the residuals of his model as a function of distance, are there any trends? If there's a trend, then that'll map into the source. And so I don't know whether, and so we talked about it last time, and Jack was going to do that. I don't know whether he's completed it or not.
So I'm the one to blame on that. He gave me the data. We haven't looked at it yet. But,
So the question is that really a source effect, or could it be an attenuation effect? And until you've looked at the residuals as a function of distance for earthquakes of different depths, you can't really reach a conclusion because they're equivalent. He He's essentially hardwired one attenuation model to fit every single one of those earthquakes. And any misfits to that model can easily map into anything else.
Yes, so that's something we're going to look at very soon. I just need the 5 minutes on the phone with him to understand his file. Yes.
And I'm trying to think back if he was going to also plot error bars on these. Did we talk about that?
I don't recall.
Because there are error bars on some.
Okay.
But then not others.
Okay.
And, if we took...
But yellow, there's an error bar in the yellow one. Where don't you see?
Oh, there are.
I don't believe the error bars, because the error bars are all predicated on the underlying model being correct, right? It's easy to calculate an error bar, but whether that actually represents the uncertainty is a completely different question.
Yeah, that is a good point.
It must be
for the depth
too small, right? It has to be. When you say an attenuation, is that the Q term, or is it the geometrical spreading, or?
It's actually both,
yeah.
But I think of the two, the geometric spreading is the more important. But if you look at individual earthquakes, the attenuation model that works for an individual earthquake, there's a lot of variability there in the correct attenuation from one earthquake to another. And so all of those things will map into the source if you have a hardwired attenuation model that you're driving through the data from every earthquake.
But that would, and maybe you said this, but that means that in order to, for example, get this trend that is being plotted, stress parameter versus depth, there would have to be a corresponding or a correlation of attenuation versus depth.
That's right. Yes, yeah, and I think that exists, right?
Yeah.
That if you look at residuals, attenuation residuals, that there is a depth term in there.
Okay, now, but just to continue on that point, so would that should also show up for the other regions, or is that just because we're not sampling and we don't have as many samples?
You've got more deep events in Quebec.
Yeah, in eastern Quebec,
yep.
Right? I think. Yeah, if we could.
So I guess the bottom line is there is something that we're seeing there, right? And it may well be a depth-dependent stress drop, because, as I say, I would find such a thing quite satisfying. But I'm not yet convinced that that's really what it is. We're seeing something, but I'm not sure that we yet can draw a definite conclusion what it is.
I can't hear.
Can you go to the slide for the West, NGA-West 2? Yeah, that's it.
Okay. Walter, you want to ask a question while Joseph is digesting
what I was going to say is that if you go back to the previous slide for a second. Could you go just for a second?
Okay. Sorry, Joseph.
We'll come back.
This one?
The one that you've had up for a while. Oh, that one there, Eastern Quebec. Okay, you can see the amplitudes fall into two groups. Depths that are greater than about 10 are generally shifted up, and depths that are less than 10 are, on average. You have a line through it, so it biases us. But you can see all of the high stress drop values begin at about 10 kilometers. Now, I would agree with Gail that, Rob, if you look over here, this is a discontinuity in the middle of the crust. As you bring your source down near that discontinuity, it becomes like a specular reflector. It becomes a really efficient reflector, and you get lots of, as she said, the apparent geometrical attenuation as you approach that boundary between the upper crust and lower crust, which is at 20 kilometers, as you bring that source down towards that boundary, you get a different geometrical spreading because you're getting a very strong mid-crustal reflector. And I think that's a factor. It's not the whole story, but it could be a factor in the pattern that we're seeing.
Well, would it also be, I'll say as a statement, I think it would also be possible then as you go into different material beneath that level that maybe the source physics are different as well.
Well, now let's go to the west, please. Then, okay. So, Gail, my question is that do you see the same thing that you just mentioned? Is that
I confess I don't know the details of those studies, so I don't know whether, in fact, they have also looked for attenuation residual trends as a function of depth.
Yeah, I don't know. I
think I know what she's done. They look at residuals versus distance and so forth after they've done this, and there isn't a trend, but it hasn't been versus depth in the short distance. So I think it's not there. But because one of the issues, we keep seeing a depth dependence, but I mean it's very strong in the West data. But do all of our studies suffer from the correlation of geometrical spreading in depth that we haven't dealt with? Because I think that might not, it's not just the East, it's all of them have done that when they build their models. We don't say, I'm going to change that term as the depth changes.
Yeah.
So these all might be wrong for the same reason, or they are all showing you a consistent with. Right.
I will check. I think for this NGA West 2, they may have limited the distances.
It was to 20.
20?
Yeah.
Right, yeah. So,
but that's where if there's you could have a bigger effect of what's going on.
No. I mean, so they as a way to try to make diminish the influence of other effects like attenuation or distance effects being mapped in and things like that.
So Norm, which is related also to Z TAR, right?
Yeah, this is the same thing for us.
Yeah, they have plots and it shows the same trend.
Yeah, but for NGA West, okay, if we're talking about California earthquakes, there's a classic study by Hoxton and Shear and others in which they looked at like 30,000 earthquakes in Southern California. There's no depth dependence in their stress drops. In other words, when they plot that versus when they show that those figures as a function with depth, they see no depth. There are regions in which the stress drop varies, but they see no depth dependence. And Hardebeck and Hoxton, when they looked at the ones that they were looking at, where they started to see a depth dependence was for there looked like there was a separation, as you pointed out already once, that there looked like there was a separation once you got below about 15 kilometers. But until you got down to 15 kilometers, they found no depth dependence.
But that, I think that can be also magnitude dependent. This is for large, that's what we saw also. Obviously, if you go to smaller magnitude, I think I agree. But this is for larger magnitude.
Rob, I mean, are you convinced by these two plots that there's a depth dependence? I'm not convinced.
It's hard, and this may go back to what Norm's saying is, we may have some biases.
We all want a depth dependence to be there. We've wanted a depth dependence to be there ever since the year after the Saguenay earthquake happened and blew all of our ground motion predictions out of the water, and we were looking for a reason. We said, aha, it was a deep event.
But when you look at these, so Walter, if you say on the left, 5 kilometers and less, what's the average? Don't look about the scatter. What's the average? And then look at the average from 15 to 20. Do you think those averages are the same? They're
referring to the upper plot, you could argue that you could put a horizontal line through the upper plot.
Well, yeah, and in particular, I think if you take off the very shallow events,
right?
I mean,
okay.
Well,
but if you don't know whether the attenuation is allowed to be depth dependent in that study, you have no idea what that plot means, and it becomes irrelevant whether the linear trend is significant or not, because you don't know whether it's truly a source trend or whether it is a attenuation trend that's mapping into a source trend. So that's what we really need to get to the bottom of. So it's almost more helpful, I think, if you look at well-recorded events and you go one event at a time and you find the best attenuation model for that particular event so that it has no residuals, and then look at its implied source. If you plot those source terms as a function of depth, will you see those same trends or not?
The other thing that came to mind, I'm not exactly sure how to verbalize it, that's why I didn't put it in my notes, but I'll try to state it, and that is, the Brune model is a very simplistic model of the source, and it, maybe it works well in some cases, but there's no reason to believe that it's going to work well in all cases. And so maybe there's something else that's going on that the model is just not able to accommodate. Why or how that would systematically map into a depth or an apparent depth dependence, I'm not sure. But, if something else is going on with the source physics, say for example, the deeper events, maybe they have shorter rise times or, faster rupture velocities or something like that, which may mask into an apparent increase in Brune stress parameter.
Hey, Rob.
Oh, yeah.
I wonder if you might be able to get a third plot like this from Europe. They would have done a lot of research on this topic.
From Europe?
So I've seen similar types of things from the Swiss studies there, but they all suffer from the exact same problem. We're not getting anywhere because they assume a geometrical spreading and use it for all of the events. It sounds to me like that's the fundamental issue, and if we don't do what Gail said, it makes the most sense. Event-specific geometrical spreading, optimize the stress parameter after that, and then see what's left. So if you only use, you have to use enough for earthquakes that are well enough recorded so that you can get their own geometrical spreading out of it, then I think you have a chance to be looking at something clean in terms of what the source is doing.
Right.
The only thing,
Yeah, Yanye's actually done quite a bit of that, so we can maybe pull some of that together.
I think one thing you have to be careful about the magnitude norm. If it's a small magnitude, intuitively I can see there's no less correlation. So what I'm saying is what you just said, you have to at least have two magnitude ranges.
Okay. So we have some action items to get that done. I'll type it for you. Okay, so that's good. We're in time for the break. 5 minutes late, so that's good. Let's start in 15 minutes. Have some coffee and chill and cookies, I think. Okay, group, party time is over. John Ake is disturbing the group. We're starting. Man, it works. It works all the time. Norm, pay attention. Okay, so one thing I wanted to do, so I skipped my little, I had a few slides to show on the database that I skipped. What I want to go over is show you all where the data is in the NGA-East data set relative to our regions, okay? So this is our Gulf Coast, including the Mississippi embayment. The red stars are the earthquakes, and the blue circles are the stations. So basically here I'm showing the black lines are the paths that are captured in that region, okay? So that's, things are only contained within this region as defined earlier by Mooney, Chapman, and shown by Gale. If we look at the central U.S., including Canada, this is a larger region. There's more events and more stations and more paths covered by that. But a lot of it, as you can see, the beautiful array here, if they're all like almost equidistant, it's a TA array, okay? Then we have the Appalachian region. We do sample the paths pretty well. I mean, given the size of the region, we can have fairly long paths here captured. And finally, the Atlantic coast. If we treat them separately, and we're going to look at regression, looking at only data within a given region to try to see if we can see differences in GS, geometrical spreading, and Q, and things like that whenever we can. So we'll do separate regressions. That's what we started doing. And I think the results that Norm showed should have only been for region 2, right? Or lumped. The data that Norm showed this morning, was that for only region 2 or the combined? Yeah. Okay, except Gulf Coast. Yeah, but my point is that when it was not Gulf Coast, was that 2 or 2, 3, 4, 5? What? I'm not, he is.
So this is Justin. There was, when it wasn't Gulf Coast, it was separated into the other subregions. It was not.
You see, I didn't pay attention this morning. I didn't watch.
There was Mid-Continent, Appalachian,
okay,
Atlantic Coastal Plain,
okay,
and then the crossing paths were all
okay, good. Thank you.
Regions.
Okay, that's good. So these are the clean, pure regions, the 4 regions, but then we combine also. So that's what we call the combine. It's everything where we have path crossings within those 3 regions, again, excluding the Gulf Coast. And then we have to deal with whatever is left is all the paths that are crossing through Gulf Coast and other places, so that's what's left. That's not contained within a region or within any of the, It means that there's a path crossing. Either the station is outside of our regionalization, so that's a question. Should we just extend the regionalization, or I don't know where the band here is limited by the geography here. I excluded that station, of course, because it samples the paths. It's in the Bermudas? What island is that? Anyways, it's a beautiful place with palm trees, and we should go there instead of being here. But these are the other paths that are left there. Oh, palm trees here, yes. Okay, so we have palm trees here, so we should be happy. Okay, so I'm going to put somebody on the spot that doesn't like to be put on the spot, but do you want to ask your question publicly? You know who you are? Okay. No? Walt, you want to ask a question? Sorry. Oh. He has a question on regionalization. I think it would be better brought to the whole group.
Walt Silva, I guess I have no choice in the matter. I was wondering why, or the motivation for having the upper Mississippi embayment now included in the Gulf Coastal region. Previously it was not, just basically the lower Mississippi embayment, but there's a fairly large difference in structure between the upper and the lower Mississippi embayments. And it would be good if we could have some sort of explanation for the inclusion of the upper portion of the embayment. Looks like it goes up to Cairo, Illinois even, where there's almost no sediments, 100 or 200 feet of alluvium.
Walter? Thank you, Walt.
Yeah, that's a good question. The embayment, the Mississippi embayment region, the Mississippi embayment Gulf Coast region is the most complicated region. So it's the most difficult one to make these decisions on. I mean, nobody argues where the Appalachians are because the Appalachians are a very clear geological and tectonic feature, geologic feature. However, the northern Mississippi embayment is very unique in that it's underlain by a high velocity lower crustal layer with a velocity of 7.3 kilometers per second, which is not something that you find throughout the rest of the central North America, the other regions, CNA. So it's not what meets the eye, Walt. It's something which is deeper. On the other hand, you could say that, well, you know, the shallow portion of the northern Mississippi embayment doesn't look anything like, you know, Galveston, Texas, which has got all these sediments and thinner crust. So it was this common characteristic of the deep velocity structure that created that region. And maybe Martin would like to. I would say that for this, you know, you could subdivide Mississippi embayment Gulf Coast region more easily than you need to do, for example, for the Appalachians or the Gulf or the Atlantic coastal plain. So it's a difficult region, very difficult region. Martin, do you want to?
Well, I agree with what Walter says there. It's mainly a region where you have extensional tectonics taking place, a little bit of maybe crustal thinning, and a higher velocity lower crust. And it changes a lot. I mean, the difference between southern Arkansas and southern Louisiana is huge in terms of the crustal structure. So it is a very variable area.
And I'll say one more thing, Walt. The area that is included, that knob that goes up, that extends up towards Illinois, is very well measured. We included it because we had a lot of data, and it was very clear that it was different. So we didn't really have much of a choice in that respect.
Larry has a question.
Can you just repeat what is Walt talking about in geographically right
it's
here?
It's right here.
That thing.
Mississippi embayment. Yeah, it's where Chris and Sharam are posted.
I just wanted to add a little more background. When the outline that you see there was determined in the 2013 work, we double-checked the work from the 4 years of work from the source model and the seismic tectonic zones that were defined as part of that study, with everything that went into that, with all the input. And it aligned with what was coming from the direction of the ground motion perspective as well as the source perspective. So the suggestion was accepted that we should, you know, draw the boundaries that essentially were confirmed.
Yeah, so that's one set of figures I didn't show that maybe I can just put on tomorrow or send to people who are interested. But taking the CUS, SSC regionalization, which is much smaller regions in terms of sources, overlaid on our regions. I sent that to the TI team, but did not share with everybody. So yeah, the little lump there is included. Okay. Anyway, so that's the data that's available for these regions. And I guess next, Martin is going to come and talk. Unless there's any questions on regionalizations, I think we have covered the questions. People are falling asleep. It looks good. Okay, cool.
Okay, so what I'm going to show you, most of you have seen most of this before. It's work in progress. Right now, we're going through to make sure that we don't have any substantial biases in our estimation of the site terms that we're getting for the Gulf region. And so again, I'll show you some residual plots and so forth that give you an idea now of what's involved in that process. Okay, so this is a geologic map of the southern United States, and you have an area there in southern Texas and Louisiana, all the way up into Mississippi embayment, around Florida, and then up the Atlantic coast. It's kind of light in color. That's where you've got Jurassic and younger sediments in the subsurface. And the area there, coastal Louisiana, coastal Texas, and Alabama, is on a very, very thick stack of post-Jurassic sediments. It's mainly marine sediments, and it's along the coastline there. It's as much as 12 kilometers thick. And beneath that, the crust is highly attenuated. It's been extended, and so when you do that, you thin the crust, and then if you take a column through there, you've got a denser than average crust, and so it tends to subside. And it's been doing that in the Gulf coastal area ever since the Jurassic. So now we've got this huge, thick sediment pile on top of attenuated crust, and the result is that we get very strange things happening to the propagation of LG. So that's showing you where the stations, for the TA stations mostly, in about 2011. At the same time, we had a series of earthquakes begin in Oklahoma and Arkansas that gave us a pretty good database for investigating wave propagation in that part of the world. So those are the earthquakes shown there as circles. There's 16 of them that we've used here, and they're scaled to magnitude. The largest one was the November 2011 earthquake, Prague earthquake in Oklahoma. And most of them are in Arkansas and central Oklahoma, but we've got 3 of them there elsewhere, one in the East Texas Basin, which is important, and then another one down there in the Gulf coastal plain down in southern Texas. Now, I just want to show you what happens when you compare 2 stations, one up in northern Missouri and another one down in southern Louisiana from one of the earthquakes, the Arkansas earthquake, February 28th. The 3 plots there, there's three channels for each of those stations. The ones that have the largest amplitudes are the station to the north. If you look right below it, you'll see 3 more seismograms. That's the station in Louisiana. So you've got a terrific difference in the amplitude of the high frequencies in particular from those 2 stations. And also what the vertical lines on the plot are showing you are the windows that we're using to extract the LG arrival. Everything I'm going to show you is going to be based on the Fourier analysis of the LG part of the seismogram. And in order to do that, you have to come up with a duration model for that, and that's what you see there, the equation there. That TD is 8.7 seconds plus 0.026 times the distance. That defines the duration for the LG part of the seismogram that we processed here. And that, of course, changes with distance. It gets a little bit larger as distance increases. I'm going to use a really simple regression model. The AIJ term there, that's the Fourier amplitude spectrum, and it's corrected for an assumed source. That's S sub I for the ith earthquake. And G there is a geometrical spreading model. We've looked at 2 different forms of the spreading. And then on the right-hand side of the equation, the R is a source term for as a function of frequency. We do regressions for 11 selected frequency bands. And then we have our anelastic or distance-dependent, frequency-dependent attenuation, where we have Q and then the V is the LG velocity. The two geometrical spreading models only differ in the spreading out to 60 kilometers. In one case, model 1 there falls off as r to the minus 1.3, and then for the other case, it falls off as r to the minus 1. Now, the receiver term is important in this case, and basically what we estimate now is a receiver term for each site for each of our 11 frequency bands. And it can be related to kappa. And it turns out that that seems to be a fairly promising approach to modeling what we see down in the Gulf. Down there below the equation with S of F, that's the source term. It's a Brune model, and we're going to assume two different values for stress drop. We'll look at 100 bars and 50 bars to see how sensitive our estimates of kappa and Q are to different assumptions about that stress drop. Now, you'll notice in the source term there, I don't have a radiation pattern term and I don't have a free surface term. Those two things combined should result in about a factor of 2 amplification. So the site terms, the R terms, should be, if you exponentiate them, they should be somewhere around 2 if things are working correctly. Okay, this table just shows you the estimates of Q that we get for all the stations down in the Gulf region for the two different spreading models. Over there on the left, you see that at 1 hertz, it's about 350. And on the right there for model 2, it's about also about 350. So there's very little difference in our estimates of Q versus the two assumptions of geometrical spreading. In other words, they give the same answers. And it's also the same, very insensitive to our assumptions about the stress drop of the earthquake. The open circles show you the estimates of Q as a function of frequency for the 10 megapascals or 100 bar stress drop, and then the 5 megapascals, 50 bars. Very little difference. So because the distances of these stations, most of them are fairly, 70 kilometers or greater than the source distance, away from the source, our assumptions about the stress drop and the geometrical spreading don't really affect the estimates of Q. Now this shows you the estimates for the site response. It's a logarithm of the site factor, basically, as a function of frequency. Over on the left there, you see the result for Model 1 geometrical spreading, and on the right, you see it for Model 2. So you see that there is a big difference in those site factors. But also the thing to notice is the shapes are very similar. It's just the amplitudes that change as a function of the geometrical spreading model. So it turns out now that if you take the natural logarithm of the y-axis and plot it versus frequency, you get your familiar kappa type decay. And this is just showing you now the result when we average up the site terms for all stations that are south of about 33 north latitude. That's down there near the Gulf Coast, way down there in that section near the coast. And it turns out that the value for kappa that you would estimate if you fit that with a straight line is about 100 milliseconds, which is a really, really big value for kappa. And this now shows you the contours along in the region there. You can see right along the coast of Texas and Louisiana the sediment thickness, post-Jurassic's, everything above the Luan Salt. It's about 14 kilometers thick, and then it tapers down to a feather edge up there up in southern Arkansas and on up into the embayment. Also, it's indicated there that you've got a big change in the crustal thickness. Something fell off.
Difficult. So you want me to give you a talk?
I just need visual aid here. All right, thank you. Thin crust along the coast, thicker transitional crust on up in northern Arkansas, or northern Louisiana and East Texas. And so if you can remember this, now compare that with this. This is the kappa estimates. And they're very strongly correlated with the thickness of the sediments down in that region. You can see that we've got really big triangles right along the coast, and then smaller triangles on up to the north where the sediment thickness gets a lot less. Our site factors, basically the zero frequency intercept of our kappa curve is pretty much independent of that. So if you just plot kappa at all the stations versus the sediment thickness, this is what you see. You've got a pretty good linear correlation there between those two things. In fact, you can fit it with a little equation where you can estimate kappa, a site kappa, as a function of the sediment thickness. And this is what our intercept term looks like. This is just a factor. Now, this is a frequency-independent factor, and you can see that it's a little bit greater than a factor of 2. It's about 3.1, and that estimates basically what you can consider to be an amplification factor of the whole sedimentary section. And there's a lot of scatter in it, but overall it's about a factor of 3. And just to go back now to look at the time domain seismograms that we saw previously, just to reinforce the idea of just how big the differences are between a station to the north and a station to the south from an earthquake in Arkansas at a distance of about 500 kilometers. That's what it looks like in the time domain. This is what it looks like in the frequency domain. You got a factor of 200 at 10 hertz. And so the question is now, how do you account for this? How do you model it? And what I'm going to propose here is that we use these kappa estimates that are dependent on the thickness of the sediments to generate our stochastic simulation, our target spectra for those. The red spectrum there is for a station in Missouri, and then the green one is for a station down in southern Louisiana. And the dashed line is just the result of the regression model that we've developed. That would be our stochastic target spectrum for the Fourier amplitude spectrum for a station down there in southern Louisiana from a magnitude 4.7 earthquake. It fits the data pretty well. It's a little bit high, but overall it's got the right shape. Now, I've been doing this, again, I say this was work in progress. I've been going back through all the data and making residual plots to see if we've got any systematic biases that we need to take care of. And so I'll run through this real quick here, these 16 earthquakes. What you've got is a plot that shows you the, for each frequency band from 0.25 hertz down to 11.2, you simply got the model residual here, observed minus calculated versus distance. And so if these plots center sort of in the middle of the band there from -2 to +2, that's the difference in the logarithms, observed minus calculated. If they center around that, then we don't really have any biases. They should just be dots. That represents a residual at an individual station versus distance, but they're connected because I had to plot it in SAC rather than in some other program. And I couldn't turn off I couldn't make dots, I had to make lines. So that's why they're jumping around. Just imagine those as every little intersection you see there is just being a dot, then you get the picture. So this is earthquake 1, and you can see that down there at 8 and 11 hertz, it's the observed values are bigger than the calculated values. They should be centered there around 0, and they're not in that case. Now, this is one of the worst examples. If we go look at the second one here, things are a little bit better, but it also is kind of overestimating what's going on. The observed values are a little too big in the mid-frequency band. They're around 1 hertz. Third event looks pretty good. The fourth one is another one of these pathological cases. It's a little bit high at low frequencies. But as we go through most of the rest of them, except 6 here, it's a little high too, in that kind of around 1 hertz. Pretty much the rest of these, and particularly the bigger earthquakes, are more or less unbiased. Certainly they don't show a strong bias with distance. And we can go through. This is a big earthquake. This is a Prague earthquake, about a 5.6. And we fit it really well compared to some of the others. Okay, event 15 and event 16 are a couple more that we've got some bias. And event 16 in particular now, its values are low relative to the model. So we have about 5 cases that we need to look at in more detail. Okay, I've just shown you now the spectra for these, for a selected few of these. This is the Arkansas earthquake in February of 2011, and this is a station Z39. It's in northernmost Arkansas. It's on only 2 kilometers worth of sediment, so sediment thickness is small there. And then the blue curve is showing you the model, and then we have the 2 horizontal components in the red and blue curves, and then down below that the pre-signal noise. And you know, it's a pretty good fit. Kind of overestimate the amplitudes up there above 10 hertz, but in the range from about 1 to 6 or 7 hertz, we're doing pretty good. Here's a station further to the south on thicker sediment, 5 kilometer thickness. Still a pretty good fit. And then here it is down there on the coast on 12 kilometers of sediment. So we have a, you know, we're capturing some of the behavior here at least. Maybe overestimating things a little bit, but doing a pretty good job. So that's the Arkansas earthquake. Probably about 12 more of these things are going to have similar fits to this. In other words, they're going to be agreeing with the earthquake, with the observations pretty well. This is the case for that earthquake in Texas. This is the one in East Texas. And you can see that we systematically overestimate the data above 1 hertz. That's at a station on 2 kilometers, and here it is on a station basically on rock almost. This is right at the edge of the coastal plain. And the shape of the spectrum is matching the data very well. It's just that there's a static, you know, a constant factor there of about a factor of 3 too big. And so I'm thinking at this point that this earthquake's moment magnitude estimate may have been overestimated a little bit. We need to go back and look at this. Bob Herman got 4.8 for this when he did the moment tensor inversion, and the USGS fellows got 4.3. So the truth may be somewhere in between. And so that might explain why we're overestimating this. So to conclude, we know that LG attenuation in the Gulf is strongly, you know, it's very strong attenuation from sources to the north of the Gulf Coast region, to stations in the Gulf Coast. And it shows a very strong correlation with the thickness of the sedimentary section. And we can estimate a distance-dependent Q. It's about 360 at 1 hertz, and it has a fairly steep frequency dependence. But that's not what's causing the attenuation. The attenuation is apparently connected to LG blockage and just attenuation through this very thick sediment section. And we can model that successfully, I think, by using something similar to a kappa approach, where we have a sediment thickness, or kappa naught would be a function of that sedimentary section thickness. So I think this has some promise. We need to make sure that we don't have some biases hidden in this that we haven't uncovered yet. We need to go back and check some of the magnitudes that we're assuming for a few of these earthquakes. But I think that this is one way to deal with this very unique situation down in the Gulf. So thank you.
Those are really big kappa values, right?
Yeah.
I'm not sure what to make of them. Is that really all just damping through the sedimentary layer? Is that
No, I don't think so. It's a combination probably of disruption of the waveguide caused by the lateral changes in the crustal thickness, plus the anelastic absorption.
That is consistent with what you've seen when you ran the simulations on the regionalization, that you saw that there was a difference in ground motion. That was, even we didn't have any sediments out there. There was part of that you could attribute to that, right? Okay.
Yeah, hi, this is Linda. I may have missed this, you may have described it, but so is this the kappa plus the site amplification? Is there a trade-off?
Yeah, it's
okay.
in there, yes.
It's in
See,
there.
the kappa is an estimate of the slope of the site terms, of what I call receiver terms versus frequency. That gives you the kappa value. But there's also the intercept value of that curve, and that's a site factor. That's in this case, I estimated it at about a mean value of about 3.5. So if you use the model that I've got here, you're accounting for the effect of kappa, the attenuation, if you would, up through the section, plus the amplification that you would get coming up through that section. In this case, it incorporates a factor of about 2 just due to the free surface effect.
Two comments, Martin. One, it's interesting, the Q that you get here, you didn't talk much about the Q, but the Q that you are getting now is very similar to the Q Gale and others get for the mid-continent. In the say 1993 and 2004, the Q in the Gulf was very different from the Q in the mid-continent. But now that you introduce this kappa term, they agree.
Yeah.
The other comment I was going to make is some more query in Hanford, particularly Linda in Hanford. There's a very strong correlation between sediment thickness and kappa. So in that sense, and physically, it kind of makes sense. You could argue the value as norm is, but it does make sense that there should be a proportionality between thickness and kappa. Mm-hmm. Sediment thickness and kappa. And you see it here, and we saw it in Hanford.
The other thing here, too, is that there's a strong correlation between the sediment thickness and crustal thickness. There's an inverse correlation. The thicker the sediments, the thinner the overall crustal section. And so we've got more than one. It's not just simply anelastic attenuation at the site that's going on here. It's just that this sediment thickness is a good proxy, apparently, just empirically, to take into account both LG blockage as well as this attenuation that's got to be happening just down there as well.
But wouldn't the LG blockage go into Q more than into kappa?
Well, it's going to cut off the LG amplitude broadband, across all the way across the spectrum. But it's also going to affect the sediment thickness is going to affect the highest frequencies the most. So you combine those two things, and you've got something that correlates with sediment thickness. Kappa sediment thickness correlation that seems to capture what we see in the data.
Yeah, surprising.
Yeah, it really is, because it's complicated. It's a very complicated wave propagation problem, and it really is amazing that it seems like that you can model it using something as simple as this.
I'm going to ask you, Gabe, so because you seem to be following what Martin's talking about. You're basically, what Martin's saying is sediment thickness works as a proxy to explain a bunch of stuff.
That's correct.
Right? Yeah. We're now calling that stuff kappa.
Yeah.
Is that right?
Yeah.
And so,
right. Well, the parameter that we're using to model it, we're calling kappa.
Okay, so that's all right. But is this, it is from the slope of the Fourier spectrum. So is this the same thing we are normally talking about in kappa, or is this something different? I'm a bit lost.
It could be different, because again, there's always a trade-off between Q and kappa, but it is the fact that it shows that very strong proportionality to thickness suggests that it's kappa, but as Martin said, it could also be that it's inversely, there's some inverse correlation between the crustal thickness and that thickness, and so what is an LG wave propagation effect,
but
maybe showing up as kappa.
If we define kappa as the slope of the Fourier spectrum, that's what you're getting, right?
Yeah.
So it must be, but it's back to now its physical cause isn't what we've been thinking about for when we traditionally talk about kappa. Is that right?
No, yeah, exactly. That's, well, you would only know if you had an instrument down below. But the other thing is, Martin, how was your sampling of distance? Was it very narrow or was it broad?
I'm sorry, I didn't hear.
You know, in terms of the distance ranges that you had. You had a bunch of stations all over
the distances for the stations that you use.
Most of the stations are beyond 200 kilometers, but for the earthquake and the important earthquake, the one there in East Texas and also in southern Texas, that's why these things, I really got to check for bias in those cases. They've got some stations in that are pretty close, and they show the same effect. They show very high attenuation.
Okay, and you have a broad range of distances.
Yeah, well,
that helps.
Yeah, but we only have two sources down there where we have substantial data inside 150 kilometers, and they're the critical ones. If we can't model those accurately, then we can't really trust all this because it wouldn't handle a local earthquake. It would work well for earthquakes up in the New Madrid area, up in the Ouachitas, but it might not. It might fail for an earthquake near a site in the Gulf, unless we can get consistent results for those two earthquakes that we're looking at down there.
Yeah, so I guess what I'm wondering, and I need to digest the study in more detail to understand, is whether it's possible that what is mapping into kappa there is really a Q effect. Is it truly path? Is it truly not a distance dependent?
The way I've done it here in this little simple regression model, the only distance dependent attenuation gets mapped into Q, into the Q term. The kappa estimate is distance independent. It doesn't have a distance associated.
So what if Q depended on sediment depth? Right, and you have an analysis that doesn't have a sediment depth term in Q. Could it be then that that's mapping into kappa? Because kappa and Q both have similar effects on the spectrum, right, in that they cut high frequencies.
Well, right there is the model. You see,
right.
The R term doesn't know anything at all about distance. It only knows about, it's just a side effect. You just measure independently for each side. And it also doesn't know anything about sediment thickness. In the regression model, there's no thickness, there's no distance. It's only a constant value for a given frequency.
Right. So what if Q was a function of sediment thickness?
Going back to the question, I don't know, Gabe asked maybe on the distances, because when you do your inversion, if you span different distances at once, then you're sure you're not mapping Q into this kappa. So that's the thing. It would be helpful to really see that. Yeah. You tell us, so we'll believe you, but it would be nice to see it.
Well, all I can say is that I've looked at a whole lot of different models, and I've put in models that had the thickness term in it, and try to solve for a Q in the sediments. Things begin to trade off when you begin to do that, and so what I've done here is that I've fixed the source, and I'm using the absolutely simplest regression model to try to capture the behavior, and if nothing else, I've eliminated a lot of trade-offs, but there may be some biases that are floating around in there as a result of those simple assumptions.
One potential problem, I'm sorry, Gail, this is quick, is that your sediment thickness may be correlated with distance, right? Because the wedge is thickening as you go.
Right, the source is in the same place.
That's exactly right, and that's why I made these plots here.
Right.
I've got a whole set of plots just like this where I'm looking at the residuals versus sediment thickness as
right.
well.
So, and I can't really read those plots, I'll confess. I'm scratching my head over them. But what I'm wondering with is if you took the dependence that you found for kappa as a function of sediment thickness and built in a function, just arbitrarily put it in, that had that same form in some way into Q. So if you went back to your regression equation and instead of having Q in the denominator, you had a function that, was basically had a sediment thickness term in there, and you assumed that was the functional form for Q. I'm wondering whether it's possible that if you parameterized it that way, you would end up with a kappa that did not depend on sediment thickness. In other words, I'm wondering if you could just as easily have put all of that effect into Q if you parameterized it that way.
Well, you would have to have the sediment thickness term in there, and then you would estimate. You might be able, and I've tried this actually, you might be able to get an independent estimate for Q in the sediments as well as Q along the crustal path. You'd have to have a distance-dependent Q, and then one that's dependent on that's a function of the attenuation that's associated with the other Q would depend also on the thickness. So you'd be estimating two Qs.
Right. So you might have something that had a form like, Q equals QA plus HQB.
Yeah, I've done that, Gail. In fact, I could show you a PowerPoint that's got the results of doing that. Somewhere I've got it on my computer. In fact, I think I showed it maybe last year, or a model just like that.
One other comment in defense of Martin. Doesn't it make a lot of physical sense if you have a material with a constant damping ratio that kappa is proportional to thickness?
Yeah. Yeah, it is. It should be.
It should be. So it does make physical sense.
I think, this is Linda, I think we're all anchored in the idea that these big thicknesses, don't contribute to kappa, but we're seeing that. And I think Ken has written about it in his 2009 paper. We definitely saw a correlation with sediment thickness at Hanford. And I also think that there is always a trade-off between kappa and Q. I mean, kappa is basically the result of what you make as an assumption on Q. So,
what I was just trying to understand is the potential correlation, because what you said all makes sense. The numbers just seem really big, and that's what I'm struggling with.
Well, the numbers have to be, the kappa values have to be big because we've got a factor of 200 in the amplitude here between the station on Rock and one down in Louisiana. They have to be big numbers. But at least there has to be a lot of attenuation somehow in the model.
But if there is correlation of sediment thickness and distance, is some of the just basic distance attenuation being mapped into kappa or not?
It could be. It could be, but we've got a few data points that are at relatively near distances that show very, very large attenuation.
Okay. I think that's important.
And those are the two important ones. Those are the earthquakes down there in the Gulf near the coastline. And one of them was the one I was showing you where I was mismatching the overall amplitude of the spectrum. I've got to figure out what's causing that. I think it's just simply the fact that Bob Herman got a little bit bigger magnitude estimate for that one than may have been the case.
It's a 2012 event, right, is it?
Yeah, it's the May 17, 2012. It's the Timpson, Texas earthquake.
Yeah, we don't have
it. It would help if we could see those plots plotted like as points, because I can't really, I can't tell what's there.
I'm going to have an extra request.
Yeah, I'm sorry about that. I threw this together earlier in the week, last week. So
I do have a question for you on the. So if we apply this as a kappa and there's a there's also an M factor that goes with it, the factor of 3 something. What is our new reference? Are we about at 1,000 like we talked before?
Well,
because again, we need to apply this relative to something in terms of application.
Well, one thing that might work, or one possibility, would be to reduce that site factor a little bit, and reduce the kappa value as well. And see, we can estimate what the kappa values would be for the stations that are on thin sediment, say like about a kilometer or two. And we know what the velocities, the shear wave velocities are in that kind of a section. That would be similar to what you would have, say, up around Memphis or someplace like that up in the embayment. And the shear wave velocities are around 800 to 1,000 meters per second.
But
so you could basically subtract off that component of it from this result, and then you could imagine then that the model that you created by doing that would be appropriate for an outcrop of, say, material at a depth of about a kilometer with a shear wave velocity around 1,000 meters per second.
But what are we going to do in the middle where we have those very deep sediments? So again, the idea of the reference rock here is something you start to do your site response from.
Yeah, that
and
would be
so
the idea.
Now you're defining the rules for the edge. But what are we going to do in the middle of the Gulf Coast?
Well,
we still need a reference.
For this very deep section, you would just use this model and treat it more or less as a linear material.
Okay.
So what is the plan on this issue, TI team? No, what I'm saying, TI team is going to evaluate.
Okay, so the plan on this, what's the plan? 2 weeks. No, it's 2 weeks. The time frame for plans is 2 weeks or 2 years or 10 years. So Martin is still working on this, and our idea here for the TI team was to use the proposal by Martin, but it's still in development. So we need to assess that and follow through with the questions and see, because we need to find a way to treat the Gulf Coast. It doesn't make sense, at least to me, to have a reference rock of 3,000 meters per second and say, hey, there you go. You do 45 kilometers of site response. So that's why the idea with thinking about that a few years back was like, okay, how can we find an adjustment that will work for the Gulf Coast with a new reference rock or reference and kappa? And that's what we need to converge on this. That's a task the TI team needs to work on.
I have a question for Martin that just crossed my mind, and that is that when you looked at those, the earthquakes in Texas, okay, were these induced? I mean, okay, so
Probably,
these.
yeah.
What about the ones that? Did you look at the ones that were in Alabama? There were a couple in Alabama that were like 3 or 4 years ago that were fairly good size.
I don't remember those. Right?
Okay. But so the induced. The reason I asked that question is that, ignoring the kappa values and all the rest, the corner frequencies you're getting in your particular model here is somewhere between 1 and 2 hertz. So the stress drops are going to come out basically with those sort of magnitudes are coming out somewhere around 2 to 3 megapascals, not 200.
Well, I don't know about that. I mean, it's estimating the stress drops for these earthquakes is difficult. And
well, you have a corner. I mean, if you get the kappa, you have to, to get the kappa, you have to, you're fitting that spectral shape. So, and you're fitting it with a Brune type spectrum where you're modifying it by kappa. So when I was looking at those figures there, I noticed that the corner was always, if you got a kappa, let's say like 0.1, then your F max is on the order of 3 hertz anyway.
Yeah.
And so you're rolling over. So if the corner is back in there, it could be, it might be higher in the sense that the kappa affected it, but it didn't look like it. I mean, one of them had that one in Arkansas had a very clear corner where it went and flattened out.
Yeah. Well, probably the best example is that 5.6 with the 100 bar stress drop. That's the ones I was showing you. The corner frequency for that is right around 1 hertz.
Yeah.
And then it just rolls off like that due to the absorption that I built into it. somehow this all has to be consistent with the data. You know, have to go back, and that's another bias that I need to check for.
Well, the one thing I was wondering about is whether or not we're biased. I mean, we talk about, you know, using stress drops, and clearly, you know, like what Rob showed earlier, you know, but all that was up in Quebec, northeastern U.S., et cetera. So if you talk about stress drops, and we're going to talk about something in close to this region in Louisiana and Alabama and Mississippi, it may be that there's a completely different stress drop regime.
Yeah. And they're probably induced earthquakes, and they may have very low stress drops.
Right.
I might be wrong about 100 bars, but I know that 50 doesn't bias the estimates for the kappa.
Right.
But now 10, you know, it's going to start.
We haven't even talked about depth, and that's a joke, by the way. Okay, Ken.
Yeah, so in that equation you have for kappa 0, the intercept is 0.04 seconds. So that's, you know, that's typical of a soft rock in California, but it, you know, it seems like that's not appropriate for the material below the sedimentary stack in the east. So it looks to me there could be some bias there.
That intercept value down there, it's about 0.05 for a 1 kilometer thick section. And I don't think that's too much out of line with what we've got for places like Memphis and places like that, you know, in the embayment. I might be wrong about that, but
yeah, but that's still a kilometer of very soft sediments in Memphis. Yeah, it's about 0.06 in Memphis, but it can all be explained by that kilometer of very soft sediments. So, you know, so your 0 intercept means basically, you know, the very northern end of the Mississippi embayment, for example, where the sediment thickness almost goes to 0. And I don't think others have found that. I couldn't find my 2009 paper here, but I have a depth model in there as well, which I think goes much closer to 0 kappa at 0 depth. But you might want to check that, by the way, in all of your.
Yeah, it's 0 depth. The intercept value is 0.04, I think, at 0 thickness. But the fit is through data that is all on sediment, at least a kilometer thick. So to the extent that 0.04 or 0.05 represents a section, say, in the Atlantic coastal plain or Mississippi embayment that's about 1,000 meters, then it seems consistent, at least to me. Maybe I'm just remembering the numbers wrong.
Other questions and general considerations on the treatment of the Gulf Coast? This is we have to treat it differently. So.
The sediment depth a parameter that you have in your flat file for the Gulf Coast? I think you have to add it in. I don't know who, but it's got to be put in there if it's.
So, okay. What? Yusef, you have to pay attention. If the project manager doesn't pay attention, you're all allowed to stray. So the question was, on the flat file, do we have a thickness, sediment thickness? We don't. So Yusef is going to put it in. He just volunteered to do that while he was talking to Ralph, so that's good. So, but that's something we could consider. You put that on the items that we can get resolved within 2 weeks. Norm, you're not allowed to ask questions anymore. So, yeah, where would that come from? So while everybody's here, okay, you have your, okay.
Oh,
it's in the PowerPoint presentation. If you were paying attention, Christine.
The best map. Yeah, the map to use is Amos Salazar's. He's got a big plate 3 in the GSA memoir on the Gulf of Mexico basin. It's a large-scale map, and you can digitize that very easily.
Does anybody here in the audience has that digitized that we could query the database instead of starting from Walter? You have that.
I can give it to you right now if you want it.
What if I give you lat long and you return the values? No, I'm trying to optimize. If he has it, he can query it. Okay, good. We'll find a way.
Because
I'm
Walter,
trying to delegate.
your database has all that in it, including sediment thickness where it's there, right? So the question is what form, and your database, I know you've got all that in an ASCII file, right? And you've got programs for extracting that information.
But I think that the most important question is what he considers sediment and what we consider sediment. I think we have a big mismatch there, right?
Yeah, so we normally are trying to distinguish between, Grenville, crystalline rocks and sedimentary accumulations, rocks that are deposited by rivers and things like that. So we don't consider limestone, which has a velocity, a P-wave velocity of 6.3 and an S-wave velocity of 3.5 kilometers per second, to be a sedimentary deposit. That's hard rock, good hard rock. So our definition of sediments is based on the velocity rather than what a sedimentologist would tell you is a sediment. So it's it's compacted. It's either loose or compacted sedimentary deposits.
But whatever.
And yours.
Yeah.
Yeah, that's what
I'm sorry.
That's okay.
But whatever Martin used was correlated with the ground motion, so that seems to work, right? What parameter did you use for your sediment thickness?
The thickness of the post-Jurassic section in the marine sediments, and it's probably exactly the same thing that Walter has in his database. But the actual map that I used was the one from Salazar.
We just need to define what we consider. Since, Walter, in your database you have velocities, we could just define a velocity that's what we call sediment above that, right? Right.
Yeah, we define sediment as rocks that have a P-wave velocity less than about 5.4 kilometers per second. So it's not not a crystalline rock.
Okay.
As long as we're clear. It's also not a limestone. It's also not a limestone.
Okay.
Now this map, of course, goes well beyond the. This includes Salvador. It's all of North America. So this map, when I made this map, I also got sediment thickness information beyond the point crustal database, because you can see it's a lot of information offshore, borehole and stuff like that. This is published in JGR and was part of a complementary study. This is more detailed than we know about the crust. This is everything that's known about the sediments from any source, borehole, size.
You need the microphone, Youssef.
So can you include both numbers from Martin and numbers from?
Absolutely. Well, Martin has he has a map. We need to digitize it. So yes, absolutely, that's fine. We can.
Somehow Martin used ground motion data and digitized the map. Those must have a file that already has those numbers in it associated with the station.
Yeah, I've got that. Mm-hmm.
Okay. Okay. Well,
it's rounded to the nearest kilometer, but I've got that.
We'll take it.
It could be refined.
So other considerations for the treatment of the Gulf Coast, the Gulf and Mississippi embayment. Because again, the rest, we do have more ground motion data to constrain our regression models, that and the prior. Or is there another valid approach we should consider that has not been discussed here for dealing with the thick sediments and the Gulf Coast as a whole, which is thick sediment and thin crust?
boundary starts to become an issue for us in terms of how do you, if we draw that boundary and say in what is described as the Gulf Coast, there's now an additional parameter, sediment thickness, what happens when you step across that line?
Yep.
And how do we make it work? Hey. It'll be our new border, right? We'll just lop that part off.
But it's possible, Norm, that, you know, as you go across that boundary, or that basically what it's doing is the sediments are in fact thinning out, so that it may just naturally smooth across there. It's not like there's a discontinuity necessarily.
Yeah,
no, but when we model it, we need to do something with it.
Oh.
But it's part of what Ken was getting at. At zero thickness, there's still a cap of 0.04. Is that the same thing that you would be using as you went into the mid-continent? So that's going to give us, it doesn't smoothly go to a cap of 10 milliseconds or something like that.
Linda, pay attention.
And we're also, I mean, the other discontinuity there is a different reference that we're discussing.
Yes.
And so the sites that have one building on one side of the border and one building on the other side of the border will have issues.
Yeah, and to me, this discontinuity and side effects or reference is harder to deal with than just crossing percentage path through a region.
Yes.
What's your solution? Gabe wants to talk. It's a good thing you always talk, not as a member of the PPRP.
Well, can you throw these into side effects? Or with some guidance to the people doing the side response? And assume that the 3 kilometers per second are so many kilometers down?
So the original idea was to come up with a different attenuation for the region and then provide a correction stack to go from 3,000 to whatever, using the work from Martin, and say to 1,000, and then provide that guidance as side effects instead of having that in the ground motion model itself. So I have everything for 3,000 and then have a set of corrections for those regions with deep sediments. Then it simplifies the issue that Bob just brought up, because we focus only on what's left in terms of attenuation, and everything else is site, knowing that in your implementation it's going to be done in 2 steps: adjustment, then site corrections, or site response. Larry? No, this way. This way first. Yes, sorry.
Larry Salomon. That's exactly how we thought of handling it.
Wait, can't you? So people the voices go down?
That is exactly how we thought of handling it in the 2013 work, is to separate it.
As far as I know, you don't have a correction.
No, well, we were thinking that you would have the 3,000 reference point, for the reference rock. And then the amplification above that would be left in terms of a site-specific task.
Yes. We're trying to propose something where we provide some guidance instead of letting that blindly or just... But yes, I understand. You have one attenuation.
The caution there is that you've got multiple sites with multiple conditions with geologic conditions that may be in a regional model may be difficult to really capture.
Somehow I can't hear you, and I cannot believe I'm telling that to Larry Salomon. can't
Okay,
hear you.
I'll
Okay,
say
no, please, just repeat
Okay.
straight in the mic. The batteries are
when
dying.
you get into site-specific work, it becomes more complicated when you're trying to consider it in a regional model.
Yes. Bob?
I mean, if we're going to do it in regional, we're going to have to put in how to gradually fade this away across the region. It can't just be a step function, because we'll be arguing about the border forever. So, the rules will have to get very more. They're not very simple. If you're here, you do this, and if you're over here, you do that. I can't see it working that easily.
If the GMP modeling part is constrained on, say, we all use the same reference, right? Then it's if you use a person path. Yeah, of course, you talk about the specific boundaries where these things will be applied. But are you talking now about the regulatory guidance or our implementation?
I'm talking about a model that can be used inside of a regulatory system, which is the product of this study.
Yes. Point taken. Gabe Toro. He doesn't need to say his name anymore. We know his voice. It's good.
One other comment, and this relates to a comment I have made earlier. Because the Q model is almost identical to the mid-continent Q model, then it may be that the issues of percent path and so on become less important. And you essentially throw all these Gulf effects into the site response, again, with a lot of guidance, because, again, I think your average geotechnical engineer will not know how to model effects a few kilometers down.
So that's an option for the TI team to consider. Okay, well, is there any, we're ahead of schedule. I tried to pad this with so much time for discussions. It's good. Okay, so, Norm, did you have time to write this all up? Okay, so we're going to go with the summary of the day. Okay? Yes. 5 minutes. So the PPRP is meeting now? Yeah, but they're meeting. They want the time anyways. Okay.
Yeah. I just wanted to see if we missed anything.
Okay, cool. So that's that one? Let me put it on the... You're going to modify it, right? I think we're good. Okay, everyone. Okay, group. We're going to start with the summary of today.
Go ahead and put it in big, and we'll see if we need to.
Okay. And maybe I can type for you, and you
Yes.
get the questions. Okay, let me get your mic.
All right. All right, as we get started here, we've tried to capture not what was presented, but what was discussed so that we have the main things that came up. If there's something that you brought up that we didn't capture, please speak up and we can, and Christine will add it in there. So running through these CAPA, we just are dealing with making sure we're consistent in how we deal with CAPA in the estimation and the application, in particular for how side effects are removed. We're going to be sticking CAPA into the FAS model as a parameter because it's easy to put in there. And then you could have adjustments if later on you chose to have a regional or site-specific CAPA as opposed to just the reference 006 value. Next. Anything on CAPA before we go on? We didn't spend a lot of time on CAPA. That will really be an October topic. The initial regression, one of the things that comes up is how you treat that fictitious depth, and that we simply need to pay attention to how that scales for small magnitudes so that we get a reasonable working model. As Nico suggested here, what we're doing is really a Bayesian approach anyway, so why not do it properly? And we will talk to Nico about doing that so we can get that implemented. I think that's fine. And don't see anything else on the.
You look at me.
I'm sorry. Anything else on initial regression? You saw what the numbers are. We're getting the minus 1.2, which seems about right. And so the things seem reasonable compared to what we had seen in other sort of current versions of models. Getting something close to what Gail had, so we must be on our way. All right. Duration. So this is a bit more of an issue. Trying to get a consistent peak factor model that's used throughout all of these models. We are using then calibrated or model-specific duration. So we're talking about adding duration into that set of correlated parameters that all fits together as part of one model, and they may not be the same from model to model, and that's okay. The problem we're going to really have is extrapolating that to large magnitudes outside our data set, and that we're really working with path durations empirically in the East, and we're going to have to do something else to bring it in the source duration, some other physical thoughts or basis for how that works. Some physical, I put here something physical, such as source dimension to help us on that. That's done all the time in the SMSIM, so it's nothing fundamentally new, but we want to really be sure that's extrapolating right.
Inversion to application. If we do the inversion using certain peak factors, the way we're going to use it in a forward sense has to be consistent. So it's for all the methods.
We're looking
inversion, to get the duration condition on a specific RVT form, we want to use it in a forward sense the same way.
So look, I think the RVT group is dealing with that, so we will just have one model there and not argue about that.
Peak factors. Let me spell it out.
The RVT peak factor, it's a parameter. There are different ways you can get at it, and their RVT group is working on that. The other thing, is a single duration as a function of magnitude and distance really the answer? Does the duration model become frequency dependent? If it's empirically calibrated, it may not be the same. Or is it stress parameter changes to it? Is it correlated with other stuff? Right now, we've been traditionally working with a duration model that applies, for given magnitude and distance, it applies to everything. But that's part of what we need to check in this whole empirical calibration.
Please give her the microphone, someone. Gail is trying to talk.
Just pointing out that Bob Herman has used frequency-dependent duration, as, of course, Norm knows for years.
Okay, anything else on duration? No, okay, next. The results, so the comment here was be sure to publish both sets of models, the Fourier spectrum models and the GMPEs, so yes, we will do that. Okay. We do need a name, so if you have a better name for Fourier spectrum models, that's a catchy name, we'll consider it.
Fame. For models.
Equation.
Equation. Fame. The fortune is in your pockets.
Let's push on so we can get out of here. How are we defining it right now? In the there's some questions of how we're dealing with the two horizontal components. What has been used is H1, the horizontal component squared plus the other one squared. Okay, then half of that in the square root. That's what has been run right now. The H1 and H2 are as recorded, and that's nice because it's invariant to rotation. But thinking about it, I'm not so sure this is consistent with our treatment of sigma in the RVT, and I want to think about that.
That came out of the RVT group, but let's bring that back internally in the RVT group to make sure this is still consistent.
So for the site terms, Justin is going to check the number of recordings per site for each of those site codes for the estimates, as well as the VS2S for each of the site codes. So we can see how those different approaches for the proxies are doing in terms of their ability to predict the ground motion.
Question, are you really looking after the phi S2S or the delta S2S here? If you're looking at the site term.
VS.
You're looking at standard deviation. Okay. Okay.
So this is more than I want to go through here, other than this is the issue that we're going to have for how to deal with the unreliable data sets and how we would center that model. So we had a discussion of that this afternoon in terms of how you can do the regression, separating out the reliable and unreliable sites, and still get some amplification factors that bring us back to an understood reference rock condition.
Yeah, that was more or less a summary of our approach for that. Okay.
Regionalization, okay, so how robust is our conclusion that there are only two zones? So I think we should check things like did you feel it intensity data just to see if these are not inconsistent with our assumptions, and then we can move on. The Q models, the question came up, that's what was used in the testing were very similar Qs, and have we missed something because we didn't take sort of the most extreme Q models or sets of parameters that were out there currently considered. The other part was azimuthal path effects, I think was coming up. How do we deal with those? They're not addressed in the median. Our assumption is we're capturing path effects in the standard deviation. Right? That's our, whenever we don't model it, we jump up and just say it's in the sigma, right? And then we can move on. Are the azimuthal variations or differences we see in the East different than in other regions? Because part of what we're trying to do is to take sigmas that we'll hear about tomorrow or Wednesday from other regions and apply them to the East, and is that an applicable or a correct thing to be doing? Anything we missed on those topics?
Okay, this was it.
No, everyone's just about worn out. So, depth dependence, we talked about this. This is sort of one of our bigger issues. why such a strong depth dependence in eastern Quebec but not seen elsewhere? And is this really depth dependence, or is it something else that is correlated and trading off? So we talked about whether it's a geometrical spreading model that could be trading off with the depth scaling, and at the end here that Gail's student will look at using event-specific geometrical spreading and then backing out the stress parameter to see if there is a depth dependence left after you start to do that. And then the next one. So this was back to if other regions are showing a depth dependence, why don't we see it more commonly in the eastern U.S. data? And probably all of these studies suffer from the issue of correlation of the geometrical spreading and the stress drop, or depth dependence of stress drop. Anything else on this? This is one of our bigger topics to make sure we didn't miss a key thing.
Different magnitude ranges should be investigated.
So CAP should put on there for check different magnitude ranges. Just put it under there.
On these? Okay,
yeah, that's fine. So there's a sort of the magnitude 4 to 5 range, or where do you see it in different ranges? Because we've seen differences empirically in the West. That's what I think Youssef is getting at here.
If I go back to the previous slide, though, we're still going to look at both right residuals.
Yeah, that was for, just put that as a sub-bullet, that was what we're going to do using a different geometric attenuation model.
Well, we can just take his residuals with distance
okay.
and see if there's a trend.
With distance,
yeah.
Okay.
The goal is to achieve the same thing as the other bullets directly.
In a faster way, yeah.
Yes.
Understand what Tom Hanks did with for the West?
Put it on the next page.
Yes.
So.
Understand the constraints in their modeling.
Yeah, constraints in with Baltay and Hanks for their constraints or assumptions, really.
Yes, assumptions for
their stress drop estimates.
Oops. Check.
Okay.
Okay.
All right. Almost there. So then Gulf Coast, that was a lot. Boundaries for the Gulf Coast, so Walt was asking for the justification for that extension, and we need to, I think, talk about that. Kappa in the Gulf Coast, there's a whole bunch, so I have a 1 and a 2. I was trying to summarize what's going on, but there are issues of fundamentally there trade-offs with other parameters. Is there something else going on that is mapping the effect into kappa, or is this a robust feature? The bottom line there, sediment thickness correlated with distance. It is to some extent, but then Martin said he still sees high kappas even for, and I put here, I'm assuming sparse or few recordings, but those at short distances still show it. So that would suggest that this isn't a correlation problem with distance, but really something that's there.
And Martin, do you agree? You're going to provide plots? Cool. So Martin said...
That's a very important point, and it boils down to the 2 earthquakes that are in eastern Texas.
Okay.
And how they fit the data, how they fit the model.
How about this issue of, is that on your next slide? Induced versus...
Well, I put on the bottom there, stress drops in the Gulf Coast are these different than the average, and this gets to the whole induced versus non-induced, but I don't know that we can answer that.
No.
I think that's a year.
Gail?
I mean, that's not been proven yet, but I think the work that's been done to date, I think there's enough work done that it seems unlikely that there's any systematic difference in stress drop between induced versus non-induced earthquakes.
Yes, but it's something we're not going to look into.
It's a bigger
in this
problem
project.
than we can take
Yes.
on.
Yeah.
The one thing you could do in the end is if we can get classifications of the events as induced versus non. If people have ideas, they can look at the residuals themselves.
If we know for sure.
I don't think there's an agreement as to which are which, right? You would need multiple.
There's multiple ways to look at that in terms of ground motions,
yeah.
in terms of, I don't want to promise doing that. It's a big task.
Yeah. Won't happen under our schedule. Right?
Not NGA-East one. Okay, so then that second slide, then we'll see if we missed anything.
So just replotting those residuals versus points, Martin, so we can see it. That will be helpful. Adding the sediment thickness to the flat file, right? So we're going to see Walter's results, and also just the values that Martin is currently using in his data set. So that should be a fairly quick task. And if we're going to deal with this sediment depth, we're going to have to still address some rules of approaching the boundary. That's always a problem. Reference rock in the Gulf Coast, so 3 different approaches were discussed using 3,000 meters per second, and just leave it up to the site response people if they deal with it. So the other, use a different reference rock that better fits the conditions in the Gulf Coast, or use 3,000 but provide a generic amplification based on sediment depth that gets them started.
Mm-hmm.
All right, so it sounded like that third one was more what may make sense, but we need to figure out what we can actually take on in this work. That's it. Did we miss anything that any of you thought had mentioned that you wanted to see captured in what we wrote here?
I would suggest the first one might be the more likely one, where you use the 3,000 and leave the site response task. So, because the other, it's after 8 o'clock now. Use maybe the first bullet might be the more appropriate one to really look into hard, as opposed to third, because it may complicate your life to try to do that in a regional model.
That's something we'll look into. We're just trying to see right now, we'll look at that, at those options. Is there any option that's been missing? Is there things that said, we'll look into this and we didn't write down, that you suggested at this point? Okay, we're good. Yep. So, good? Observers. So, people who have not had the opportunity to talk yet or ask questions, that includes the JMC if they didn't act as a resource expert, or all the other knowledgeable people stuck in the back of the room. Questions, comments? Okay, so tomorrow morning we start at 8, not 8:30. There's going to be food here. I'm not sure exactly, probably at least half an hour before. I'm sorry, I didn't check the food schedule. So we start at 8 tomorrow, and now we need you guys to get out of here and have fun tonight and get some rest. And everybody online, if you have registered to log in tomorrow, it's a separate login. If you haven't registered, you need to email us, otherwise you won't get in. Thank you, everyone.